Good morning. Welcome to this final event of the SciLake projects, From Fragments to Insights, Making Scientific Knowledge Discoverable. I am Stefania Modeo. I'm an engagement and training officer at OpenAir. And in these past 3 years, I had the privilege to lead the dissemination and communication activities of SciLake and work with many partners who are here today to showcase and discuss our results. So while people are joining in, I see that the number of attendees is increasing. Feel free to introduce yourself in the chat if you'd like. And in the meantime, I'll walk you through the agenda. Okay, so we will start with an introduction of the problem of scientific knowledge and fragmentation, having a look at what was the SciLake project journey. Then we will have a first panel on turning scattered knowledge into living knowledge graphs, a short break, a demonstration of the SciLake tool through pilot case studies, another short break, and a second panel on unlocking hidden patterns in knowledge graphs. And we will close the event at 12:30 Central European Time. While I would ask you during the presentations and the discussion to share your questions and comments using the Q&A channel in Zoom. This will help us track and address the question in a more efficient way. So we will use the chat for the introductions, for logistic matters, and also to share useful link. But please, for the for addressing your questions, go to the Q&A channel. I think that, yes, this is a good moment to hand over to our project coordinator, Thanasis Vergoulis. Stop share. Okay, so I hand over to Thanasis. Thanasis is a principal researcher at the Athena Research Center and the SciLake project coordinator. So Thanasis, the floor is yours for the introduction.
Thank you, Stefania, for the introduction. I hope that you can see my screen.
Yes, we can see it.
Okay, great. So, good morning, everyone, and welcome. My name is Thanasis Vergoulis. I am a principal researcher at Athena Research Center in Greece and the SciLake coordinator. It's a great pleasure for me to open today's final dissemination event. This was a long journey for our 3-year project. Over the past 3 years, the project brought together researchers, engineers, and domain experts from various domains with a shared goal to advance the way we manage, connect, and query and exploit scientific knowledge in the era of artificial intelligence. When the project began, the landscape of artificial intelligence was already evolving rapidly. And the SciLake project started its activities in this evolving landscape. I would like to say before starting presenting the journey of the project to thank again all the project partners that participated and make this journey possible, but also all the project experts and the external experts that we have invited in this final dissemination event to discuss and celebrate the project outputs, but also the wider theme of making scientific knowledge discoverable. And with that said, I will start my presentation with the motivation of the project. So the situation in the research community was that due to the research activities in every uh, discipline, there is a large volume of scientific knowledge that is available for everyone to use and discover. However, due to various reasons, for instance, because scientific knowledge is scattered across diverse sources beyond publications, in datasets, protocols, methodologies, software tools, and workflows, but also because it is um, encoded in different and diverse formats. Um, all this creates some barriers for experts from different domains to identify useful knowledge and to use it to reveal insights that are relevant to their research. At the same time, we all experience the overwhelming volume of research objects that exist due to various reasons, because the research community has become bigger than ever, and because there is a lot of pressure for researchers to publish not only publications but also datasets and other research outputs. This more or less creates these conditions that although we have a vast amount of scientific knowledge available, it's not always straightforward how to find useful and valuable insights for your research or to make informed decisions. SciLake is a project that aimed to address these challenges by developing a toolset that would help researchers and domain experts to organize and query scientific knowledge, enabling them to discover insights and make informed data-driven decisions. And this toolset supports the creation of dedicated customizable environments for analyzing scientific knowledge, and we call them scientific lakes in the context of the project. So what is the SciLake concept? We use a diagram like this in most of the project-related presentations. So the idea is that at the left we have the domain knowledge consisting of different publications, other kinds of reports, databases and knowledge bases, knowledge graphs that already contain domain knowledge in a particular format that is not always very structured and easy for the machines or even human experts to identify it. So the idea is that instead of searching inside this vast knowledge base by themselves, domain experts provide the corpuses, the databases, the knowledge bases to the scientific lake, and through an array of different important transformation components, the system is able to ingest this content and encode the useful, valuable contained knowledge in a structured format. We have used the knowledge graph technologies for that, and create what we call in the context of the project the domain-specific scientific knowledge graphs. So we have also provided some conditions of these knowledge graphs so that when they are created, they will be aligned with well-established standards in the scientific knowledge graph community. The most important is that we are trying to make them compatible to the SKGIF standard that has been developed in recent years by the Research Data Alliance. So that we make sure that these graphs that are created in this concept, they are easy to combine or easy to query in a particular way. Then, when we create those knowledge graphs, we take advantage of knowledge graph technologies, knowledge graph management systems, like graph databases, for instance, to make those graphs easy to query and easy to access. So the concept also includes an array of components that are targeting accessing and querying the graphs. And then, on top of this scientific lake concept, it is easier for developers to create value-added services. In the context of the project, we have selected to have two value-added services to showcase that the scientific lake concept can work in practice. The first one was a knowledge discovery service that takes into consideration um, citation network analysis to facilitate the discovery process. And the second one was a reproducibility assistance service that enables searching for reproducible studies, but also flags outputs that are not reproducible so that the researcher is aware and have an option to enhance them in a way to improve their reproducibility. Now, the scientific lake itself can be considered as an environment, a customizable environment that uh, has deployments of components uh, to import and transform scientific knowledge into the system and to make this knowledge easily accessible and easy to query. But it's not um, it's not a system that cannot be customized for different use cases. This was by design, our selection, so it is a tool set and the domain experts can select and deploy those tools that make sense for their own particular discipline because we made early on the assumption that although research domains have a lot of similarities, they also have specificities that need to be addressed using different tools or using a tailored version of them and a different customization and configuration setup. Um, so just to provide a very quick look under the hood of the different components that the SciLake environment offers, the different tools. We have two main bundles of tools. The one is about import and transformation that in the previous diagram you saw it's at the left of the diagram. Here we have a tool that can help domain experts to create their own knowledge graph based on other types of representations like databases, relational databases, for instance. We have a knowledge graph interlinking assistant that tries to identify potential links between different knowledge graphs. We have a research object recognition from text component that can help the extraction, can support the extraction of different domain entities or research object mentions inside scientific texts. We have the research object link recommendation component that provides recommendations about potential connections between research objects, like, for instance, a dataset being supplementary material of a publication. We have an article segmentation component that supports extracting the different sections, for instance, of a scientific article, an automatic translation that can support the translation of non-English scientific manuscripts in English. The Opener Connect that was used in the context of the project to create subgraphs of the Opener graph that are tailored to particular domains of interest. A field extraction component that can identify the fields of science or the sustainability development goals that relate to a particular publication. And finally, citation-based impact analysis component that can analyze the citation network of different publications and calculate some indicators that estimate the citation-based impact of the work. And then moving to the other bundle about data access and querying, we have a graph database called Avant Graph and a graph analysis engine called Graph Alg that is able to analyze large graphs and produce some statistics or transform them into another graph. We have the Lake API, which is compliant to RDA's SKGIF that we mentioned earlier and offers a standardized way for accessing the graphs by programs without having a lot of expertise in graph database query languages. And finally, we have created a knowledge discovery and reproducibility assistant portal called Deep Spaces that supports various functionalities that can help researchers to identify valuable research. And in this project, we had 4 pilot cases, each coming from a different domain: neuroscience, cancer, transportation, and energy were the disciplines that we had selected, and for each of them we had at least one community. For transportation, we had 2 communities involved that they were actively, apart from demonstrating the project components and evaluating them in practice, they were also actively involved in the design and development processes, providing valuable feedback on the service prototypes. So the project consortium consisted of 13 partners. 8 of them were focusing on technology, so they were technology providers, and 5 of them represented the scientific communities that were used for the pilots. 11 of them were research organizations, while 2 of them were from the industry. And as we have already said, this was a 3-year project. We had more than 3 years actually of project activities because we also had a small extension of 3 months. This is why our project, while it started in January 2023, it ends in March 2026. And during these 3+ years, we have published 15 deliverable reports and we had more than 13 publications in peer-reviewed journal and conferences. So with that said, I would like to also mention that in the next sessions, you will have the chance um, uh, to follow some discussions around scientific knowledge management and discovery and querying. Also, you will also be able to get some insights about some of the components that I mentioned, which are part of the SciLake ecosystem, because they will be discussed during the demonstration presentations, but also during the panels when the subject is relevant. But before going into these discussions, I would like to also mention a last thing about the relation of SciLake and the AI boom that we are experiencing the recent years. So SciLake started during the period when LLMs and generative AI became widely accessible and started enabling a lot of real-world applications. So as it is evident, SciLake was also affected by this situation. Many SciLake components were built around or enhanced by language models. And in addition, the structural knowledge that is represented inside the scientific knowledge graphs becomes crucial because it can provide a reliable context for generative AI models, helping them reduce hallucinations, among the other. So what we think is that the tools that we have delivered becomes highly relevant for generative AI approaches that are targeting scientific knowledge applications. And I think that during this event, you will have the opportunity to realize that yourselves. Having that said, I would like to thank you again for your attention to our project. I have included here my contact details in case you would like more information. And I would like to um, give the mic again back to Stefania so that she can introduce the first panel.
Thank you, Thanasis. Thank you very much for the introduction. And yes, you gave the perfect link to the panel, so we can move straight to the discussion. And in the meanwhile, I remind you that you can use the Q&A channel on Zoom to address your questions and comments. We will monitor it and also incorporate your input to the panel discussion. So with that said, I'd like to start asking the panelists as I introduce them to open their camera. Also now it's perfect. We will. So this panel is about turning scattered knowledge into living knowledge graphs, and we want to explore now how we'll start with exploring how large-scale knowledge graphs can be adapted to community needs, and also where AI and large language models can help and where they cannot, with a particular attention to aspects of trust, provenance, also hybrid workflow that keep domain experts in control. We will also reflect on what these choices mean for the research policies and the access to research and the access and evaluation of research. So I will introduce our panelists. I'll keep an eye to my notes so that I don't forget any important information. I'll start with Miriam Baglioni from the Italian National Research Council in Pisa. Miriam is a permanent researcher focusing on scholarly communication infrastructures, research data, interoperability, and open science. She contributes in many aspects of the OpenAir graph, the development and operation. And in particular, she leads the enrichment process and the dataset production. Next, we have Nicolau Duran from Series Academic in Barcelona. Nicolau is a data scientist and researcher supporting evidence-based policy making through analysis of higher education and research systems. And in SciLake, he has worked on the metadata enrichment and the knowledge extraction pipelines for the scholarly document. Next, we have Haris Papageorgiou from Athena Research Center. He's a research director at the Institute for Language and Speech Processing and also leads the AI team there. Haris has deep expertise in artificial intelligence, knowledge discovery, natural language processing, and he also has contributed as an expert in STI, science, technology, innovation policies, analysis, also in context of evaluation and assessment of research and innovation programs. And we are also joined, last but not least, by Eric Jean Girard from the French Ministry of Higher Education and Research. Eric is a data scientist working on data-driven tools to support public policy for the ministry and for the French research institutions. And he also serves on the Open Alex Advisory Board. So thank you all for accepting our invitation to join the panel. So we can start, and again for the audience, please contribute to the discussion with your questions and comments in the Q&A. Okay, so to connect with the introduction that we heard from Thanasis, I'd like to start with Miriam. We anticipated that SciLake is supporting interoperable and reusable scientific knowledge graph for specific research communities. And the starting point for this is to integrate different types of research products and other entities that are relevant to the scholarly communication. And the OpenAir graph served as the backbone for this community-specific knowledge graph. So the question for you is, first of all, if you can explain what does it mean that the OpenAir graph served as the backbone for these community knowledge graphs? And also, I'd like to ask you a comment on what were the main challenges in adapting a general purpose graph like the OpenAir graph to each community specific needs.
Okay, good morning to everyone. So the OpenAir graph serves as a backbone for the community specific scientific knowledge graph because it already integrates a wide range of heterogeneous research outputs and scholarly communication entities. The graph does not only include publication, but also research data, research software, other research products, as well as contextual information like projects, organization, fundings, and all the relationship between them. This diversity of entities and relationship provide a good starting point from which to build more specialized scientific knowledge graphs. Now, the OpenAir graph is domain agnostic. It is not tailored to any specific discipline, but OpenAir recognizes the importance of communities. So since 2016, it works together with them to provide a place where communities can find all the relevant content together, providing the OpenAir Connect service. As Thanasis said before, OpenAir Connect can be used to select the relevant entities for each community, for each pilot. OpenAir Connect is designed as a tool for open science, community building, and outreach. And it is not OpenAir does not operate the Connect service by itself. Each service, each gateway is managed in collaboration with the relevant research community. Communities can define a set of criteria that help OpenAir understand which is the content that is relevant for them. Now, specifically for SciLake, each pilot provided its own configuration, and OpenAir also introduced for the first time the idea of subcommunity, which was especially useful for the transport pilot, because as Thanasi said before, and you will see in a while, there are two transport communities with different objectives in the SciLake project, and one single gateway would not have adequately reflect their specific needs. So OpenAir extended the Connect service to allow community pilots to specifically select the subset of the broader community that was specific for their needs. Thanks to this selection and the curation process, we have community-specific subsets of the graph. In terms of challenges, the main one we had was to fine-tune the configuration to select the relevant products for each community, to define and refine the selection criteria, validate the resulting data set, and ensure that the graph reflects the actual practices and priorities of the community, required continuous collaboration with domain experts. And we had to do many iterations. Overall, OpenAir Graph provides a common interoperable infrastructure, and OpenAir Connect enable the creation of community-focused view of the graph that can be a starting point for the extension with the domain-specific knowledge of each community.
Miriam. Yes, this sets about the scene for the for what was the added value of SciLake, bringing together the scientific communities and bridge this part now of knowledge management made for general purposes to target to specific needs of communities. And so I'd like to do another round with Haris, as Haris also is a partner of SciLake, and you contributed to your tools for extraction of knowledge. Now you'll tell us more details, but so I'd like to ask you. So again, also. From your viewpoint, what are the concrete benefits that SciLake brings, and this domain-specific scientific knowledge graph brings, and especially compared to what general purpose foundation LLMs, large language models, can already know, memorize from their training data. So I'd like to open also the discussion to introduce the role of the LLMs in all of this, and also how do you see the landscape is evolving? So connecting to what Thanasi said in the last part of the introduction, what should we expect in the near future?
Hello, everybody. Thank you, Stefania, for the question. So let's see the question in its parts. So knowledge graphs, as a graph of triples, it is a structured representation of entities and relationships. On the other hand, large language models, LLMs, store probabilistic patterns in their weights. This is the model actually in LLMs. This means that knowledge in large language models is implicit. It is distributed in billions of parameters that the LLMs have, and it is very hard to inspect and very hard to update this knowledge. So knowledge graphs are very strong in terms of transparency, in terms of explainability, in terms of traceability. And this is strong aspects in a governance framework that the scientific community needs. In addition to that, we can say that graphs support a sort of symbolic reasoning. When we say that A causes B and B causes C, we can infer that A causes C as a transitive reasoning, which is not apparent in large language models. LLMs, large language models, can also approximate this type of reasoning, but are not guaranteed to do it correctly, this type of reasoning. In terms of updatability, I could say that updating knowledge in large language models, it is very hard. It is done through fine-tuning, through retraining, or through the use of retrieval augmented systems. So, in that respect, we can say that knowledge graphs, it's a very good medium of how we can reduce hallucinations. And we all know that LLMs could potentially hallucinate because they generate plausible language, not verified facts. Another aspect that I would like to mention here is that knowledge graphs are excellent in multi-hop questions. There is a ton of literature, scientific literature on these aspects, and knowledge graphs can answer difficult questions like, for example, which drugs target proteins involved in Alzheimer's. This is a very difficult question that can answered flexibly and adequately through knowledge graphs. One thing that it is very important here is that knowledge graphs have also their own limitations. They are very slow and expensive to build and curate and design. And the coverage, as we do know in SciLake, it is domain specific versus the general language that the large language models support. And they have this difficulty as if we take them as a separate entity, knowledge graphs, they cannot support vague, they cannot easily understand vague questions or conversational language. We have built specific modules in order to query the knowledge graphs in a specific language. So I think that there are merits in both parts, and the thing is that if we try to combine LLMs and knowledge graphs, as it is happening in scientific literature and in industrial developments, we can take the best of both worlds, avoiding hallucinations by the use of knowledge graphs while keeping the conversational nature of large language models. Yeah. I think that this is the way that we can see today the use of knowledge graphs in the industry. Back to you, Stefania.
Sorry, I was muted. Oh, thank you very much, Harry. So as I understand correctly, large language models help a lot in how the users can access the knowledge inside a structured format, in reading, I'd like to connect your intervention with a question for the other panelists, and maybe Nicolaou, since you were also involved in knowledge extraction technologies for SciLake and for your work. Can you also comment on how what is done about the knowledge graph? So the linking elements of scholarly data like publication, software, affiliations, author, or patents. So can we go a bit into the details of this and discuss how the core elements of the knowledge graph can or cannot be assisted, replaced by AI system, yes, and in general, which source of scientific information can be replaced by AI, and what is most relevant and critical in building reliable knowledge graphs according to your work.
Yeah, I think that from my experience, I will answer different things in different directions, because I think that these questions are complex, and have different dimensions. When you ask, or when we ask a chatbot a simple question like, "What is the population of Spain?" The system at the end relies on information from somewhere. If we expect this information to be true, or relies on structured sources from information reported by, I don't know, an authoritative source like the statistical office. The thing is that here we are talking about documents, but scientific knowledge is fundamentally relational. Basically, that at the end, scientific knowledge is not just documents that we can answer questions based on context from documents, and these relations, include relations between publications and linked datasets, software, authors, and these affiliations, organizations, papers with grant data, project, etc. At the end, or more modern links, that are becoming more popular nowadays, that linking research to policy documents or news, or media. And at the end, without these links, we have just isolated documents. And at the end, AI requires information, and the question, I think, that is, which is the infrastructure that these systems rely on to access to the knowledge. However, I think that there are some links that are originally reported by the original sources or by the authors themselves, in the publications, indicating the ORCID, ROR, the link to the software, etc. But then the problem is that there are other links that are not reported in the publications. For instance, I don't know, links to domain knowledge base of the domain. For instance, I don't know, that are allowed to discovery, or that to explore publications. For instance, there are cases like I read a paper some years ago, that this was in 2015, that there was related to the tagging of mesh terms in biomedical domain. The cost for to tag each publication by a domain expert costed $9. And one of the problems is that, for instance, in this case, there are highly curated and taxonomies in a domain like biomedicine, for instance, that there are large collection of knowledge bases, but there are other domains, some of those that we have explored in SciLake, that they have domain knowledge bases that are heterogeneous, partially curated, and creating these links between domain terminology and the research publications require automated methods. The other thing is that, but these automated methods, we use language models, different types or different architectures. The problem is that to identify those things that we don't have context enough for those terminologies, is that language models perform poorly when there is no enough context, and sometimes this information of this context about what this acronym or this code, or because at the end a code of a concept of automatization in transport from a perspective of a computer is more or less the same, without the proper definition and examples, etc. And here in this case is this domain knowledge that humans should guide and help, and this is one of the things that we have explored here at SciLake. The thing is that the other problem is that we have also to recognize that human curation is not perfect. At the end, it's not scalable, of course, And even with automated methods, we struggle, no, trying to apply automatic metadata curation tools to millions of documents, no, because at the end, the computational cost is also a barrier, no. But just to share an example is that my experience working with domain experts, annotating by hand scientific articles in 8 categories, well-defined but complex categories from a specific domain, no, the agreement between those two was 87%, no, between the two experts, because humans also bring biases, sometimes subjective interpretation, and there is also inconsistent expertise. And one of the problems or things working with humans doing some of these tasks is that we cannot track the alternative, we cannot track the confidence scores, and how to identify those errors introduced by humans, something that also with automated methods can be discovered and complemented. No, but the other main point that maybe AI is helping is in the accessibility, no, because we have been developing knowledge graphs and open research information infrastructures, no, that were exposing APIs, RDF endpoints, Avant Graph or Neo4j, the examples here in SciLake, require high technical skills to access, to query, no, and nowadays, no, thanks to, I think, maybe generative AI is also helping to democratize one of these problems that we couldn't maybe solve, no, in the past. Yeah.
Thanks, Nicolaou. Yes. I think we can move to a more like direct questions on how can we trust the system, and when so first of all, we had this interventions by Miriam, Nicolaou, and Harry's partners, SciLake partners. So I'd like to ask, everybody, but in particular Eric, as external expert, let's say, external with respect to SciLake, if you have reaction or comments about what our colleagues said, and in particular also what do you expect to find in these scientific information systems? How can you realize what does it mean to trust for you when using these systems, and in particular also when AI is in the loop?
Hi, thanks, Stefania. So maybe my first point would be to just point out that in the discussion we talked about LLMs and then scientific knowledge graphs, and especially Harris underlined that graphs could help LLMs and complement LLMs, and I completely align with that. But I would also want to highlight that we can use LLMs to build the graphs themselves. So it's slightly a different idea. And this could seem simple from the exterior, but it's not. So building the links between publications, datasets, software, even just the offers and affiliations, which is like the basic thing we expect from a scientific knowledge graphs, it's far from simple to do. And so, yeah, for sure, a long time ago it was done manually, then with different type of automation and algorithms. Now with more AI or LLMs, but still we need trust for that, because we build KPI, we build assessment out of those databases. So trust is key, and to build trust we need transparency. And when I say transparency, first thing is transparency in the outputs. So, okay, we use an AI system to compute a link. Can I see exactly the very output from the LLM, the input, the output? Okay, and so that I can build my own gut feeling out of it. Does it seem good or not? For sure, there will be some metrics for that, but generally, when people compute themselves the metric on the system they built, it turns around 99%. So I would be a bit careful with that. But I think users need to see themselves the precise output, not in the global thing, but also in line by line. So that's one thing, just see the results. And then the second part is being able to correct those. Like, okay, mainly people, what they want to test knowledge graphs, they want to see themselves. It's a mirror feature. So not the most useful because people already know what they did in the past, but they want to check if the image that is reflected of their work in the system is right or not. So, and most of the time they might detect errors, big errors or small errors. So I think they need to be able to correct. So we need kind of a feedback loop in the system to build trust. And so it's a way to get this scalability. So we use automated and AI systems to parse and to analyze millions of documents and so on, but we still need human in the loop somewhere. One could say, okay, we could use other LLMs as humans, so it's called LLM as a judge. So LLMs that kind of challenges each other. For sure, it's a way to do it, and we could maybe reach new levels with that. But I'm pretty sure that we still need humans for now at some points to keep the control.
Eric, yes, very interesting viewpoint. Okay, so for other panelists' reactions to this, and maybe Miriam, can you, from the point of view of the graph construction pipeline, can you reply to Eric and tell in general what is done in terms of trust?
I have to say, I completely agree that the human must be in the loop. And for what concerns the quality, provenance, and transparency, these are all characteristics that are central when building a large-scale scientific knowledge graph as the OpenAIRE graph. Sorry. When building the graph, OpenAIRE relies on a graph construction pipeline that manages all the steps needed for building, enriching, and cleaning the graph. Each step is documented, and the code is open science, so everything is traced. As a first key practice, we track the provenance throughout the entire pipeline. Every piece of information in the graph can be traced back to its original source or to the process that produced it. Everything starts from the collected metadata that go through several processing stages: normalization, cleaning, deduplication, and enrichment. Everything is traced. So, for example, when two or more entities are deduplicated, OpenAIRE produces a brand new entity that combines the information from the original records while keeping track of the duplicates it is derived from. So we have the new entity, but we have also the results it was built from. This holds for every information included in the graph: the FOS and SDG obtained by SciNobo, the links provided by the mining to put together results and projects or community, the enrichment phases. Everything is linked to the process which produced that information. This makes it possible to trace how an entity was constructed, where specific metadata elements originate from, and how they evolve. Another important aspect is the use of persistent identifier to anchor entities and improve reliability. Whenever possible, OpenAIRE relies on identifiers like DOI for research products, ORCID for researchers, and ROR for organization. These identifiers significantly improve the accuracy of linking and the traceability of the information across the different systems. One of the issue, let's say, we have in building the graph is that the size of the metadata that we have to handle each month is always growing. OpenAir this with hundreds of thousands of metadata, and thanks to our construction pipeline, we ensure that the same procedures are applied consistently each time the graph is built. Finally, in the context of SciLake, for example, the resulting knowledge graphs are exposed following the SKGIF specification, as Tanazit said before, and this promotes transparent data model, interoperable access. The box is yours.
Thanks. Okay. Nicolau, do you want to comment on this? If you are speaking, I cannot.
Sorry, I was mute. Yes. Yeah, maybe one of the things that related to some of the things said before by the other panelists, I think that one of the important and was a bit mentioned by Eric, that one of the challenges is that evaluating also reliability of some maybe automated tools or AI-based tools for enrichment, expansion, and metadata curation. Is that evaluating reliability at scale is one challenge. Manual curation is often seen as a gold standard. However, can contain some errors. The thing is that some of these target knowledge bases of authors, affiliations, concepts evolve in time, and then to keep these tests or collections updated is a challenge, but also that the other challenge that was this one mentioned at the end, evaluation collections for automated methods sometimes are not designed properly, or they work very well in the test environment, but then scaling to the real case, they struggle a bit. And one of the things is that one challenge is to involve really communities and actors, domain experts in the design, and also trying to build evaluation collections are more complex, more challenging. This may affect, of course, the accuracy results, but to avoid having 90%, 99% of accuracies, and then on the complex or edge cases to fail. It's something that we see. That we have also all of us developed things that then in the real case and edge case fail. And also related to this thing of the provenance and accountability, mentioned by Miriam, I think that when at the end decisions, enrichment are done by automated methods, this should be traced and documented, and explored and then corrected when it's necessary, because there is also one of the main challenges that we have also seen, in the development in SciLake is that sometimes AI, for instance, struggles when identifying none of the candidates is correct, assigning affiliations, assigning author, or assigning these domain concepts, because generally tends to be optimistic, but sometimes the other object, for instance, the target database of publications doesn't contain the citation that we are looking for, but is assigning one that is the most similar one, but not the correct one. And this is one of the challenges, and to identify these low confidence cases is relevant also to put the humans maybe to review those cases and not random cases or all the cases, because at the end the availability of domain experts is limited, and at the end not all the inputs from humans are valuable, because also I think that for instance, two good practices of hybrid human AI, to mention two things that connecting here in the panelists, the Works Magnet developed by Eric and the team, and also the OpenOR developed by OpenAir, that allow humans to curate organizations. Those things require training of the domain of the people interacting. Not all the input from individuals are valuable, without a proper training. This is also a barrier and a challenge.
Right. We have a question in. So Haris, I'll give you the floor, but I want to tie it also with a question we have in the Q&A. So first of all, if Haris, if you can open it, so you have it and you can see it. Denis Okefe Sorry if the pronunciation is probably off. So first of all, Dennis, thank you so much for the effort in explaining and exposing your question written. I know it's not ideal, but you shared a very specific case. So thank you very much for the effort of writing it, first of all. So you are talking about a specific case where you have unstructured textual data in the form of meeting transcripts, inquiry reports, social media discourse, governance, documentation. And the question is for Harris, if how your NLP work focus on automatically extracting structured knowledge from these types of sources. You have Dennis also contact who is happy to discuss. And then we have a specific example. So can you, Harris, go through it? Would you like to answer? If you
Yeah, okay. If I got it correctly, so let me stress again that as I said, knowledge graphs, in KGs, knowledge claims are grounded. This is fundamental because, as I said, LLMs operate through probabilistic inference over training distributions. And in LLMs, knowledge is latent, and the outputs, the outcome of large language models are to confidence shaped, but not truth verified. So, in that sense, we could say that the epistemic status of large language models is that LLMs are statistically plausible. The answers of LLMs are statistically plausible given the training data that we inject into the system, into the training of a large language model. In knowledge graphs, knowledge is encoded as explicit claims, accompanied, as we discussed, with sources, timestamps, confidence, and we have a lot of curation processes. So let's try to separate this language generation from truth storage, from knowledge storage. So if I could say that that knowledge in LLMs approximate knowledge through language, where knowledge graphs approximate knowledge through structure and ontologies and so on and so forth. So this is very fundamental in terms of trustability and traceability and so on. And this is very crucial because what we see lately is that there are two major trends, and this is very interesting. It is the combination of knowledge graphs and LLMs. This is something that we see a lot in the industry, and hopefully, I believe that there will be more knowledge graph as retrieval augmented systems than vector retrieval systems. And ironically, it is the use of LLMs that build these knowledge graphs. So what we see lately is that in order to speed up and streamline the process of building knowledge graphs, we use LLMs. This has also happened in SciLake with SciNobo as a toolkit of in science that extracts this kind of metadata and all these claims and scientific evidence in scientific literature, dataset software and so on, artifacts, research artifacts in scientific literature. So even in SciNobo, we use LLMs in order to build these knowledge graphs. So answering the question, in the chat, it is yes, it is. This is the best way. It seems that it's a very good way to proceed, to go ahead. The use of natural language processing and the LLMs to build these knowledge graphs and to use them as and curate them and update them, because it is, as I said, the updating mechanism is very critical here. And this is something that we can do flexibly and very effectively, and to use it as the main medium of knowledge into the LLMs, where LLMs mostly keep their role as conversational agents. So even in the agentic systems, this would be, we will see this a lot in the future. The use of knowledge graphs as knowledge as the main memory that LLMs can use reliably.
Okay. Okay, thanks. And we have another question. I see that Miriam is typing an answer. So since time is flying and I don't know how, then we are always we are already approaching the 15 minutes. I want to go at least with a quick round on the policy side. So how do we are building these knowledge graphs and yes, let's discuss at least in this last 5 minutes how these transform the research evaluation and the science policy. And I'd like to start with Eric, since you work for the French ministry. Yes.
So yeah, hopefully we could hope that maybe graphs could help to go beyond simple metrics. So analyzing how the knowledge flows, analyzing how the community evolves, what's the formation of the communities and so on. So graphs could help to do that. And also maybe graph topology, could help us detect weak signals that could have more information than just counting citations. So these are new things to analyze. And this analysis, again, I think should be done by human and not by LLMs today, because for sure we could ask Claude or whatever LLM to make this kind of analysis based on the graphs. And that could cause kind of sort of false authority, because Claude will have a very nice language, nice graphs, everything well formatted, but it can be complete bullshit. So again, experts are really needed to make the analysis. So maybe the idea is to go from simple KPIs to narratives. That's also the idea of the narrative CV. And for sure, Gen AI could also help researchers to build their narrative CV, but they need to keep control of it for sure. So again, the idea is to use AI as a tool to enhance our different processes and try to be smarter. I just want to stress one point, one risk, which I call the dead science theory. So it's like the dead internet theory. Like we use AI, well, a researcher could use AI to make their report, and assessment could be done with AI again. So no more human in the loop, just AI analyzing other AI stuff. So that would be a terrible loss, I think, for humanity. So let's try not do that. But if I want to be hopeful, we can go from just counting outputs, publications, dataset, etc. So we can keep counting, but we could try to understand a bit more in depth the structure and the dynamics of research, and this at scale.
Yes, definitely agree. Thanks, Eric. Any very final comment from the other panelists? Quick ones. we are already, we want to be on time because the morning is compact. I'm very happy of the very interesting discussion that we had. Thank you very much, Miriam, Eric. Miriam is still typing. I see that an answer is coming for Volker. So thank you, Miriam, Eric, Nicolau, and Aharis for this very insightful discussion. And we have a break now, a 10 minutes break. We are starting with the demonstration sessions. So we have 5 pilots communities from the energy planning research, cancer research, transportation. We have 2 sub-communities, maritime and automated mobility, and the neuroscience. So we will start with Jakob Reger. So Jakob, the floor is yours, and you will see. Show me. I mean, I'll show up when time is up, but I'm sure you will do perfectly on time. Thank you, Jakob.
Yeah, thank you for the welcome. So hello everybody, my name is Jakob Rager. I'm a professor at one of the partner institutes of this project, the HSSO Valais Wallis. We are a University of Applied Science. You can see normally on the first slide now all the people that helped us to get to these results. Besides, of course, all the SciLake partners that specifically worked before we applied this to the topic of energy research. So let's see if the slide moves forward. Perfect. So there you should see now the energy pilot and a little bit about our expertise. So now we'll dive a little deeper into energy planning itself. Our specialty is really energy planning and the questions that are linked to it with sustainability and implementation policy. So that's more an applied research. So we are more at the end of consuming what SciLake produces. And with the enrichment, we try to relate a little bit towards reasonings that we'll share with you now. So first of all, what did we try to do besides looking into energy? We had another second topic that is of interest or very important to us is really the part that most information has actually a geo-information, a geographic location linked to it. So estimates go to 70 to 80%. In our case, that's very important because researchers in the field of engineering tend to publish a theory and show a case study based on this theory and therefore doing applied science. And that can help then when you understand where the location is to maybe scale up a solution, accelerate energy transition, or simply optimize a solution that you have in place in your location. So with that being said, what we try now to explain you briefly, even though we heard this morning that geographic entities from institutions are already not that trivial to find, we try to push it a little further and now try to extract more or less automatically the case study location. However, we reframe it a little bit because we will talk more about what we call object of studies or an object of study. It's not necessarily always the case study, but that is what we can capture today with the extraction. So the definition of object of study is larger than a case study would be, but still compared to manually searching through all the papers to find which ones do have a geographic location and where it is exactly, it is a major advancement. So how do we do it? We have here an overview of the extraction process of the whole pipeline. So we start with OpenAir and we do select a subsection of the knowledge graph based on keywords, on topics that we can define that are linked to energy and energy planning. With that, we then really have our own graph, and we do two types of extraction, especially the one with Jordai is the one that we'll look into now. So that's the extraction that will look into the object of study, link it to the spatial database, and then allow us to show either multiple results, as you can see on the right top side on the map. So where we start to aggregate findings, let's say on a European level, for example, as we're here in a European project, or you can, of course, always look into individual results on a paper. And that's really the extraction that we get from series, and that will be explained in the next slide in my words, and later on Caesar will help me a little bit on the technical terms on extraction. So basically we have a raw span from an article. In this case, it's really the abstracts that we show, and we identify here Bern, Switzerland. You first of all can realize that maybe Bern was already written rather in the French version. The German version would be without the final E. Still, though, it was detected. However, then the second question comes up when you match those extractions to OpenStreetMap. So it's to a geodatabase that gives you the location on the map is actually which Bern are we talking about? And that's really a not very trivial question, because each case study, each object of study has traps, and for example, Bern exists in Switzerland as the state of Bern. It exists as the city of Bern. So at least when you fall into Switzerland, you're somewhat close in case that is the right extraction. Or you could also end up in the US, where the city of Bern also exists. And there the model has to be trained and make a choice. In this case here, the model choose Bern City. However, when you look in detail in the article, you realize it's Bern, the state that is mentioned. So it's close, but that's a little bit typically what happens when we look at the different cases. And I'm not going to go through all of the potential traps that could happen. Still here, we're fairly close. So it's a partial right detection, and it can help us then to do further queries that are still of interest. So for example, if we move on to the next slide, we could start to deploy really spatial searches where we would like to know whether in the Alps, for example, a certain object of study like PV in the, as mentioned in the previous example, is studied, and we can therefore then easily grab all the publications that otherwise you would need to really manually add up and identify. And I think this kind of knowledge discoveries on maps, where you could then identify different geo-entities that are located, would allow other groups that today don't really access the knowledge graphs in such a way to more easily see the added value and work with those knowledge graphs. And maybe also for the researchers that are more into, let's say, looking what can be done out of this and reaching out to, for example, funding agencies. I mean, it could be interesting to show additional links, such as papers that are linked. Well, we already have talked to about the geo entities, and you can here see a little bit the total numbers of papers that were identified, as well as the geo entities that we could find. You can link them to specific energy types, such as photovoltaic, that I'll use throughout this example, and even link into some document extraction that are linked to legal basis, so that can help us towards implementation. If I show an example result now on an extraction that we prepared, here you can see the topic of solar PV, which is an energy type that we defined together in the database. On the left side, you can see our extraction results. On the right side, you can simply see the solar potential. So basically, if you're in Southern Europe, you have higher potential than in Northern Europe. And what you could expect maybe from the findings as a simple citation count is that you will find more object of studies in Southern Europe, as the potential is potentially higher, and maybe also more government programs exist that support this kind of research. Then you see that the reasoning on the left side in our map is not 100% consistent. For example, you can see France, that doesn't have really that many publications compared to Germany that has a high number of publications on PV. Well, the difference is here really in the energy system itself. France also has a higher share of nuclear energy. Germany decided to phase it out, so is actively looking to new solutions. Therefore, you can see impacts of policy that could be linked to the citation count that we could get out of the results that are here. And so that could be a way also for funding agencies to start and think about how to structure science funding in one way, in the way you aggregate those results, and can then work towards even more specific solutions that could be identified. So with that being said, of course, as in all scientific work, and especially when you demonstrate such a first case, on our side, we are still not on a seamlessly workflow that needs to be improved a bit and optimized. We see also potential in improving the geo entity recognition. However, that's as it was indicated before, human work that needs to be done and is quite time consuming. So here we estimated around 70 to 80% of correct extractions, which I think is great for a first test of those tools. And then according to the use that you make out of it, of course, you need to consider what that impact could be in case you have either omitted places that were not extracted, or wrongly attributed papers to a wrong city, wrong country, as I showed earlier with the burn example. And finally, maybe one last step is, of course, the native graph databases do not support the geo queries. So that's why we have this parallel infrastructure with several databases that need to be linked and need to search with the different IDs to bring up the results that you could just see. So with that being said, I think we are convinced that the object of study location is a really innovative enrichment service, and that could also be applied, of course, to other fields of research. Today, in those science knowledge graphs, we think that this geographic information is generally not very present, and therefore it could help us to get additional knowledge out of it, and help also people to link towards what's in the knowledge graph a little bit better. We also see it as a new entry into a knowledge graph and open infrastructure in a larger way. And yeah, we hope that we are able to continue to work on this, so that we can also, as was mentioned earlier in the chat already as one question, integrate elements that come outside of research, such as government regulations or even procedures maybe. So with that being said, I'll stop here. Of course, we could dive deeper into some of those questions. However, for the sake of time, I'll stop and hand over to the other pilots. And of course, I remain here, and the team is also there for any questions that you might have. Thank you very much.
Thank you, Jakob. Is Cesar here? Cesar, would you like to complement a bit what? Yes, thanks.
Yes, if Jakob stops sharing.
Yes, screen should be up to you now.
Good. So you should be seeing my screen. Yeah.
Perfect.
I will just quickly walk you through the geographical entity extraction. As Jakob said, it has three different steps, which you can see here, but I will dive a bit into each of them. The first one is the named entity recognition, which is just, as the name implies, finding the geographical mentions in the text. For that, we fine-tuned a model to recognize locations, and this includes also monuments or landmarks, demonyms, you will see why. And this was done across several data sets in a multilingual fashion, and forms the basis of the extraction, which is pretty much like a very common problem or extraction method to identify locations. Then the second step is linking these locations to a database. In this case, it was OpenStreetMap, to ground this knowledge into something structured and with well-defined characteristics, and of course enrich the dimension itself with additional knowledge, such as what country the city belongs to, what is in case you want to draw a map, what is the bounding box of this map, for instance. And then the third step, which is the most important one in the sense of identifying, in this case, case studies. And as Jakub said, we are exploring one of the categories for that, was the classification of the mention within the context of the text into what role the location is playing in the text. So we have several categories. One of them is the object of study. The other one would be the location of research, when it's mentioned, not in the affiliation, but mentioned directly in the text. Then we have other like contextual references or policy regulation, and for instance, the beneficiary or impacted entity, which perhaps we could also explore, maybe Jakub agrees or disagrees, as one of the proxies for case study. And this is the reason, the main reason why in the extraction and the collection of definition of whether location is, demonyms were included, because for instance, you could be talking about a certain research impacting, let's say, the German population or something like that. And this doesn't necessarily mention a location, but it does imply the location through the demonym itself. And that's it very briefly about the extraction of geographical entities.
Thank you, Cesar. So if you have questions, drop them in the Q&A, so we will address them. And we can move to the cancer research pilot with Konstantinos Kardamiliotis. Konstantinos, I saw you.
Thank you, Stefania. I will share my screen. I think you can see my presentation now. Is that right?
Yes, perfect.
Okay, thank you. So, hello everyone, I'm Konstantinos, and I'll be presenting on behalf of the Cancer Pilot for our SciLake project. So this pilot, our main goal was to build a cancer-specific knowledge graph using the SciLake functionalities, and our main focus was on CLL, on chronic lymphocytic leukemia. The idea was to see if we can contextualize and connect information in a meaningful way and hopefully inspire some follow-up experiments. We also wanted the final output to be something that could fit into different machine learning tools and libraries, so that it's not just a static resource, but something reusable. And of course, this was a team effort, and the key people involved are listed here: Leili and Daniel from Karolinska Institute in Stockholm, Sweden, and me and George from the Institute of Applied Biosciences in Thessaloniki, Greece. So in terms of what we wanted to achieve with this pilot, the objectives were pretty straightforward. First, we wanted to make it much easier to query information efficiently from publicly available resources. We also wanted the knowledge graph to help us address ongoing research questions, especially around the molecular biology and immunopathology of CLL. And another goal was to explore how different mutations might affect the disease and see whether the knowledge graph can help highlight those relationships. Finally, once the graph is in place, we'd like to apply more advanced algorithms on top of it and try to make new discoveries, identify missing links, and reveal patterns that aren't obvious from the data alone. So here we have a quick overview of the data model that we used in this pilot. Now, what you are seeing is a set of main entity types that make up our knowledge graph. We have genes, gene targets, pathways, biological processes, compounds, diseases, publications. And the idea is that all these entities are linked in a way, and this way lets us trace how a mutation in a gene might affect a pathway, for example, or which biological processes are influenced, which compounds interact with them, and what publications say about this. Here's a schematic view of the overall project setup and what goes into the graph. In the upper left corner, you can see the various data sources we use, such as ontologies, gene datasets, drug databases, and so on. And at the upper right, there are multiple existing knowledge graphs. For this pilot, we focused mainly on the largest one, which is the clinical knowledge graph. At the bottom, you can see the SciLake tools, which take all of these inputs and integrate them to generate the cancer-specific knowledge graph. And here's where we are with the pilot right now. The knowledge graph is hosted both on a server at the Athena Research Center and on the AvantGraph platform, and can be queried with the Cypher language. We also have demos available on our webpage, and query examples are hosted on GitHub. In addition, there are complementary resources like BIP for Cancer and the Cancer Gateway that support the knowledge graph. So the system is up and running, and the infrastructure is in place for research with the right access. On this slide, we wanted to show how biological questions can be translated directly into a single Cypher language query. Here we focus on 3 questions about the gene NOTS1. Mutations in the gene NOTS1 are a well-established prognostic marker for CLL, indicating a worse outcome for patients. So the questions are here. Which drugs target NOTS1? Is NOTS1 linked to CLL through the protein that codes? And which other genes are related to this gene? All these 3 questions can be addressed in one query, and the Cypher query here matches drugs targeting NOTS1, traces connections through the protein to CLL, and also finds related genes. And here we can see the result of running our query in AvantGraph, a platform for hosting and exploring the graph. The idea is to use graph technologies to better understand the connections between entities in our data, such as genes, diseases, and publications. And AvantGraph is a tool that helps us with all of that. The purple node is the disease, which is CLL. The red one is the protein NOTS1. And the green nodes are all the drugs that target NOTS1. And also the orange, yellow, call it whatever you want, nodes are other genes that are related to NOTS1. The information about the gene-gene relations come from a dataset called BCMO, which was integrated to the knowledge graph by us. And next up, we have a subgraph that includes only proteins that is generated when you run these lines of code that are listed in the left part of the slide. Proteins rarely act alone. This network shows which proteins are known to interact with each other based on experimental studies, and the connections come from curated biological databases, and each interaction has a confidence score based on the amount and quality of scientific evidence. Using AvantGraph's native algorithm support, we then identify connected components in the network, and this finds groups of proteins that interact with each other, but not with any other proteins in the network. It can point to proteins involved in the same biological process. Now I'll hand it over to Dan, who will show how this is implemented in the query and how the algorithm is executed through the Jupyter notebook. So I think that Dan should be unmuted now.
Yes, thank you very much, Konstantinos. So hi, I am Dan de Graaf. I'm a PhD candidate and a developer of AvantGraph, which is a high-performance graph query engine that we are building at TU Eindhoven. We are one of the SciLake project partners. So to perform this connected components analysis that was just shown, we use the Jupyter Notebook integration and the native algorithm support that is included with AvantGraph. So AvantGraph supports the same Bolt protocol that Neo4j uses to send queries and to retrieve results. And this makes it a drop-in replacement for Neo4j to improve query performance, which allows you to send queries from languages like JavaScript, C#, Python, and even from Jupyter Notebook, as was done here. And a unique feature of AvantGraph is its support for user-defined algorithms through the GraphHawk language. GraphHawk is a language specifically designed for writing graph algorithms. And the native support in AvantGraph means that you can write your algorithms in GraphHawk and embed them inside Cypher queries, which you can see on the example on the screen. And AvantGraph will take care of the optimization and the execution of the query and the embedded algorithm together. So first and foremost, this makes running algorithms very convenient. You don't need to export and import your graph into external tools to perform this analysis, and you can use a high-level language that was designed specifically for writing algorithms. Furthermore, because all of the processing happens inside of the database, and there is no data movement, so that makes it very efficient. AvantGraph also applies its powerful query optimizer to algorithms, which allows me to run this analysis over the 200 gigabyte graph in seconds just on my laptop. And the results that were shown in the previous slide, they were obtained by combining these two features. A Jupyter notebook, which you can see a snippet of on the screen, sends a cipher query, which includes an embedded GraphHawk program to AvantGraph, and AvantGraph executes that. And finally, the results can be visualized using standard Python libraries inside of the Jupyter notebook. Now, next to developing these capabilities for the SciLake project, we've also created an interactive tutorial and an online playground for GraphHawk to experiment with it. It's available from the link on the slide. If any of the readers, if any of the attendees here are interested in learning more about this technology. So now back to you, Konstantinos.
Thank you, Dan. So next, Next we demonstrate how BIP Spaces enhances literature discovery using our knowledge graph. In this example, we run a query for Notch 1 and CLL, and instead of returning a simple list of papers like a traditional search engine, BIP Finder ranks publications using impact-based indicators. These indicators evaluate aspects such as influence, popularity, and relevance within a specific topic. This means we can quickly identify high-impact or influential papers, even when those papers might not rank highly in generic search engines. Additionally, the system expands queries using domain-specific knowledges, such as gene synonyms or related biological entities. So each publication in the results is annotated with entities from our cancer knowledge graph, like genes, diseases, drugs, or chemicals. And this lets researchers explore the literature in context. Instead of just a list of papers, they can see how each paper connects to key concepts, filter results, and discover relationship across publications. So some of the results from this pilot have already been shared externally. For example, parts of the work were presented at the ECCB conference last July, when we showcased the SciLake cancer knowledge graph in the context of precision oncology. There has also been a workshop and a few other press releases highlighting the project. Thank you for your attention, and if you have any other questions or would like to learn more about the cancer pilot, our knowledge graph work, please feel free to contact us.
Thank you very much, Konstantinos and Dan. We have our next presentation by the maritime transport pilot with Aphrodite.
Hi, hello to everyone, and thank you for joining today. Let me share my screen. Okay, I hope that you can see my screen now.
Yes.
Okay, perfect. So this presentation is focused on the maritime transport pilot. In the SciLake maritime transport pilot, discovery and SKG connections are enriched using external tools, and this integration helps stakeholders uncover hidden trends and gain deeper insights into maritime research. Okay, the developed services based on the needs and requirements of the main stakeholders in transportation research and more focused in maritime transport. We had the close communication and collaboration with our network here in Piraeus. And this involves content providers, research organizations, and public authorities. In more detail, content providers could use SciLake services to automatically verify compliance of exported records with set guidelines. For research organizations, the services aim to support the adoption of open science publishing practices and monitor the implementation of open science practices by their researchers. And finally, for public authorities, for example, national and international research funding organizations, monitor services are offered to control the impact of their funding within the transportation research community. The knowledge graph consists of 5 main parts: the results that represent the outcomes of research activities, of course, data sources that are the sources from which the metadata of graph objects are collected, the organizations that correspond to companies, research institutions, and public authorities involved in project, and other projects that that are relevant, and communities that are groups of people with a common research interest, such as transport research community, or more maritime or marine experts. This is the data model of the graph. As you can see, it consists of 12 nodes and 24 relationships. Actually, let us focus on the vessel type entity, which is connected to product nodes, for example, publications, and also regulations. These connections are the result of an information extraction process carried out by our technical partners using machine learning techniques, and specifically the system identifies when a publication refers to a particular vessel type, which is important. Of course, other criteria and parameters could be used. And okay, now let me demonstrate how this works in BIP services and spaces. The first scenario involves searching for open access publications after 2024 that included decarbonization as a keyword. So we select publication as the type and open access as the availability, and the results are sorted by popularity by default, and popularity reflects the current impact or attention of an article, often referred to as the hype. And this is based on the underlying citation network. If we want a chronological order, we use the year for ordering, as we can see here. And of course, the results that we receive are different. The second scenario involves searching for publications, all publications, not only open, that are referring to vessel types and include autonomous shipping and collision avoidance. And we want to focus to more important studies, and this means studies with higher impact factor. So in this case, we have a complex requirement, and written as you can see with this end. So we select publication as the type and vessel type for the results presentation. And we also select citation count to order the results. And we receive the results as you can see here. In this case, here we change the order of the results, and we use the year to see the results with chronological order. And if you check this and this, we have different results based on what we need each time. Apart from vessel types, we can select also fields of study or technologies for the results presentations, as you can see. And we have an analysis about engineering and technology, industrial biotechnology, and other. Also for technologies, in this publication here, we have the category of traffic collision avoidance systems. Overall, this knowledge graph demonstrates, let's say, a commitment to advancing research in the maritime sector by establishing, monitoring, and providing all research outcomes in the maritime transport research sector, of course, with a strong emphasis on open access resources and reproducibility. That's all. Thank you for your presentation and your participation today.
Thank you very much, Aphrodite. We have Seraphim.
Yes, hi.
Seraphim, do you want to complement?
Yes, hi. I am Seraphim Fadzopoulos from the Athena Research Center. And in the context of the SciLake project, I was involved in the implementation of BIP services. So I will comment on that. So as Aphrodite said, BIP services provides several ranking schemes to sort the search results. So apart from the options like sort by publication year or citation count, we offer these two graph-based approaches called influence and popularity. So the influence indicator is based on PageRank. That is a well-known algorithm used to estimate the importance of a node inside the network. And in our case, the influence score of a research project reflects its importance based on the structure of the incoming citations in the citation network. On the other hand, we have popularity. And the popularity indicator is computed using a PageRank variant that models a researcher that navigates the citation network while also incorporating a bias towards the recently cited papers. And it does so in order to prioritize research products with a strong current impact. So both these indicators are computed with our open source library called BipRanker that is implemented in Python and Apache Spark. And we execute it over the citation network of the latest opener graph that currently contains more than 300 million research projects. And to conclude, the resulting impact indicators from this analysis are openly released as a dataset on Zenodo, and you can download it to use for bibliometric analysis or any other further studies. So that's all. Thank you.
Thank you, Seraphim. Yes, so I'll include in the chat the link to our Zenodo community where we have collected all these data sets. I'll do this in a minute. Is there Sotiris also?
Yes, hello, I'm here.
Hi.
Okay, so I think I will briefly describe the field of science classification that Aphrodite showed. So basically, as you saw in the slides, we have we developed a tool in the SciLake project that can automatically assign scientific publications to research domains. To do that, we utilize a hierarchical taxonomy of scientific fields. Currently, this taxonomy contains 5 levels of different granularities, and it's a culmination of different ontologies that exist out there. For example, we have combined the Frascati OECD taxonomy along with EuroChivox, Scopus, and Science Metrics labels, and we have extended it using machine learning techniques. The idea here is that instead of relying on the text of the paper, the approach also leverages the structure of the scientific ecosystem, and in particular, citation networks and publication venues. And when I say venues, I mean journals or conferences. And basically, the whole system builds a graph where you can link publications with journals and research fields. And through that, you can propagate field information through citation relationships and classify publications to different fields of science. This method, in essence, enables accurate assignment of publications to research domains, and was used in the project in order for pilots to identify relevant literature and build their initial collections of publications, which then turned out to be the domain-specific knowledge graphs. I think this is it about the classifier.
Thank you, Sotiris. We can move to the next pilot, the SICAM transportation pilot with Athanasios Ballis. Good morning, Athanasios. Oh, yes, you're here.
Okay,
Hi.
unmuted. Okay,
Okay.
hello, good morning. Just
You
give
can
me
share.
a moment to share the screen. And okay, hopefully you see now the screen. So,
We see
okay.
that you're starting screen sharing, but we don't.
Okay.
Oh,
I
yes,
have a-
yes, we see it. We see
I'll
it.
probably close the video because I don't have very good bandwidth. So sorry for that. I'll close the video just to be sure that the slides roll on effectively. Okay, so the contents of my presentation briefly, we will discuss about the scope, the method, the tools, the results, and the next steps. So that, yes. And this is the schema that Thanasis already explained. So I will skip this and go to the next slide. About the scope, we want to simulate the research on the SICAM aspects. The SICAM is cooperative, connected, and automated mobility. So we discuss about autonomous driving and things like that in a few words. We want to use some tools in the routine of a researcher. So we're going to make some custom queries, find some trends that may exist, and identify some patterns, depending on the needs, on the case, and on the subject. And of course, we're going to find out if there are some novel interconnections, interconnecting some new technologies or some new ideas that pop up in this emerging field of transportation. Now, the method that we used, most of it was based on a data model. You can see the entities that are in a rectangular, like data sets.
Athanasios, sorry to
Yes.
interrupt. We see
Yes.
some black bands, boxes overlapping your slide.
Okay.
Yes, if you can
Sorry,
minimize.
I thought that they were managerial. Sorry about that.
Yeah, I know Zoom. Yeah, you have the Zoom.
Can you see it better
It
right
is.
now?
We can see. We still see the central one. The top central one is quite big and covers
Okay.
the graphic.
Just give me a moment again.
But if you describe it verbally, I mean, we can see like 98% of it. So
Sorry, I don't know how to minimize this. I'm sorry
no
for
worries,
that.
no worries. Please go ahead. You can describe. I mean, it's a minimal thing.
Okay.
No.
I cannot drag it elsewhere. Okay. I think now it's a bit better. Sorry for that. Okay. So you can see here the interconnections of the data model. Some main entities are the standardization bodies and standards that, to speak frankly, were added afterwards. So it's not part of the model that was created, but instead we were based on publications on some scenarios and technologies. Of course, we also take some information from projects and datasets. And you can see the interconnections with the relationships between them. So we created this data model, and to do so, we targeted some projects and some papers that were focused on SICAM. So our case was very targeted, and we tried to exclude the noise as best as possible. And of course, we used this input to the technical partners to proceed with their developments. As Miriam discussed earlier, this is the open-air subgraph. It was created for two transport subcommunities, one of which is ours. So you can see here that we can test with some keywords and make some searches. The filters are on this column by axis, by type, year range, field of science, the funder, the Sustainable Digital Development Goals, the country, the language, source, and research community. And one can sort them by relevance, dates, so citation count, popularity, influence, and impact. On this screenshot, we have sorted them by date, so we can claim that we can see which is the latest trend on a specific subject. Another tool that we use from SciLake is the BIP Spaces one. Again, you can see the filters in the sort that can be arranged. On this particular screenshot, we tried to search the LiDAR, one sensor that is widely used in autonomous vehicles, and we sorted them by popularity. Those two tools are very practical, so one can see them on the links that exist here. I think that the presentations will be available afterwards, so they can be tested. And some other tools that mostly were internally used, you can see them here. For example, AvantGraph was already explained by Dan. We can do some custom queries there. For example, if we find out a paper that is very interesting from a specific researcher or organization, then we can make some queries to filter out other papers from the specific individual or the specific organization. So this is possible through this tool. The PDF fetcher and automatic translation were some, we can say, integral tools that are not very easy to showcase today. And the last one is the entity extraction, that we use some main entities from the data model to extract from papers or abstracts or other pieces like articles. I have one slide for this one, and then I will invite Cesar to discuss a bit more on that. So we extracted some main entities like the vehicle type, the VRU type, which can be pedestrian or cyclist, the sensor type like camera, LiDAR, communication type, how the vehicles or the roadside infrastructure intercommunicate each other, the connection type, and the automation technology. This means that we have 6 levels of automation, as we say in SICAM. Level 0 is we don't have any automation, and level 5 we have full automation. One automated car, an autonomous car, can drive wherever it can go without any manipulation. So in this entity extraction tool, you can see that the driver assistance terminology has been already identified. We can see the model. It is the SICAM gazetteer in this case, and it is linked to a source from which a taxonomy was extracted, and it is based on two European projects, Symphonica and FAME. The last one is a sequence of projects that create a knowledge base around SICAM, and nowadays it is called SICAM Ambassador, just for the record. And another case, and the green box, it's the car that is linked to a passenger car with the confidence that you see somehow created by our technology partner. I think Cesar may have more to say about it. Before giving the floor to Cesar, just to mention some results. We can say that naively, if we try to Google a term on Google, we can get some results, but they are with much of noise. And you can see here that if we Google SICAM, unfortunately for us, we have an identical term from medicine, which is congenital kystic something, I'm not sure. So we're going to, and we managed to extract only the relative information. Another type of result we can say is that if we query a term like pedestrian in different tools besides SciLake, like Google or Google Scholar, we get this number of results. So you can see that they are quite too many. But if we use some SciLake tools like the Open Air Explorer or the BIP Spaces, we immediately get only some hundreds of results instead of millions. So this is the main gain from the project, I suppose. And the next step from that is that we would like to fine-tune the data model, include some more SICAM-related entities. We would like to test the SciLake environment internally within our team. And of course, another good step would be to invite internal or external researchers to test what has been created by the technical partners from the several teams that have already introduced themselves and their technologies. So I would like to invite Cesar just to mention a few things on the entity extraction tool, and I will stop sharing my screen.
Okay, can you see my screen?
Yes.
Okay. Yeah, so as Athanasius mentioned, I will quickly share the entity extraction process. This consists of two steps. So the first one, again, is the named entity recognition, just finding these mentioned in the text. We did two different types of approaches, one more shallow, which was at the level of titles and abstracts, and the deeper one in a subset due to volume constraints on full texts, where we use another of the SciLake tools to partition this text into the relevant sections. And then the second stage is the entity linking to ground this knowledge into some precise and standard terminology that exists in ideally established taxonomies or vocabularies, or as it was in this case, something made ad hoc as a mix of two different external sources. The initial process was very much a human in the loop approach, as we discussed earlier in the panel. There are some domains for which there are a lot of resources, particularly the biomedical domain, but most of the other domains in this project lacked such information. So we had an iterative approach whereby at the beginning, the experts were very involved in defining the scope of the entities of interest. And then, due to the lack of annotated data, we leveraged LLMs to generate some sort of pseudo annotations, pseudo labels that were then verified and validated by the experts themselves. So a small sample that was, as I said, validated by the domain experts. And with this, we trained the name entity recognition models. We tried different approaches. And then after this, there was a round of qualitative exploration and iterative feedback with the experts, where they decided which type of model that they found performed the best, both taking into account normal metrics, let's say numbers of accuracy and precision and so on, but also what they perceive was best for their use case. And then there is the entity linking to the taxonomy, which also has two stages in itself. The first one is to retrieve candidates from the taxonomy given dimension via the similarity between dimension itself and the terms in the taxonomy. And then the second stage is using both the candidates and dimension itself, but augmented with the context that surrounds it in the text to actually re-rank these candidates and choose the most suitable one. There's an additional layer to this, which is a gazetteer approach, which simply searches for the taxonomy terms in the text, and this is a simultaneous name entity recognition and linking, just done in one step. And as Atanasio shared, this is a quick example where we find an automation technology that was found by the gazetteer. So you can see it has a full confidence because it's an exact match from the taxonomy. And the link on the right is, again, an exact match. And then we have the car identified as a vehicle type with very high confidence with a Roberta model in this case, and then linked to the term in taxonomy called passenger car with, again, also a high confidence, but it's not a perfect match as the fully confident gazetteer approach. And that's it quickly for this case.
Thank you, Cesar. We have to quickly move to our next pilot, the neuroscience with Archana Golla from the eBrains community. Archana, you can share your screen and you can start. Thanks.
Yes, I hope you see the. Just a second. I hope you see the right screen with the presentation. Yes. Okay, perfect. Hi, everyone. I am Archana, and I work as a researcher at the University of Oslo. And I'll be demonstrating how the neuroscience pilot has neuroscience pilot's use case for the SciLake ecosystem. So the neuroscience domain includes diverse research fields whose products are shared across a wide range of journals and databases. And this, of course, negatively impacts the knowledge discovery. So with this pilot, we wanted to develop an SKG that brings together heterogeneous neuroscience research into one place. We started with configuring a gateway on OpenAir that only collects neuroscience relevant research products. The metadata from this gateway was then mapped to an interoperable metadata model that Miriam mentioned earlier, the SKG-IF metadata model, and an SKG was built. And at this point already, the research products are already interlinked based on their shared metadata and bibliographical information. And then a language model was trained with neuroscience-specific entities, and Cesar already mentioned about the named entity recognition. And so using that, the entities were identified in these research products, and then the research products were further interlinked based on shared entities. Additionally, SciLake services also provided impact indicators for all the research products, which were also then integrated into the SKG. The SKG can be accessed through the BIP spaces, and then queries can be performed on Neo4j and AmandGraph. And here's a simple illustration of a research product in the neuroscience SKG. You can see here is a research product, and you can see all the other research products it's connected to, and this is based on so this is a relationship that goes both ways. It's either the research product that is citing these, or there are other research products citing this product. And then there's also other domain-specific entities that are linked to this, like the techniques and the biological sets and the species and so on. And also in general, the metadata such as the author information and also the DOIs attached to it. So all of these circles here are individual nodes, and they are linked to other nodes with relationships like mentioned here. And hence you can imagine how all the elements in the graph are interconnected. And this SKG, as I mentioned, can be accessed through BIP spaces. And let's do a quick query. I hope you can still see my screen with the BIP space.
We can see it.
Yeah, perfect. Thank you. And yeah, let's do a quick query here. I'm trying to find all the research linked to this brain region called cortex. And And you can sort these results based on different ranking schemes provided by SciLake, and Seraphim explained earlier about these individual indicators. Let's say we want to sort them based on citation count. And here, so the research products with most citations now come up here. And the results can also be sorted based on the faceted filters, which include domain-specific entities. And when you go to the individual page of a research product, there's information, some metadata information, such as the title, the authors, and then the abstract, and also the impact indicators that the SciLake services have provided, and also information such as DOI and so on. And then all these annotations here all these annotations here show how this research is connected to other research based on shared entities. For example, here, if you click on the cerebral cortex, which is a brain region, you can see all the other relevant research that is mentioning this region. So that was a quick demo of the user interface. And going further, yes. Okay, and then we also performed some Cypher queries demonstrating the ease of knowledge discovery using the SKG. Here we queried for the top techniques in the SKG based on the number of products mentioning it. And here's a list of top 10 that we have discovered. And then in a similar way, we are queried for the top 10 publications for a specific region, medial entorhinal cortex, based on the citation count of these individual publications. So we saw that the publication that had most citation counts was about 1,600. And then we could get information such as the titles and the DOI. And further, we've also done some simple comparative queries. For example, here we tried to query for research products that are linked to different neurological diseases. And this sort of query helps users discover popular research topics. And further, the user can also try to get some information about the content of the research. So to extend the previous example, for the same diseases, here we tried to see how the gender balance is across the researchers for these diseases. So from these examples, we can already get an idea of how this SKG provides not just a platform for knowledge discovery, but also possibilities for meta-analysis. And since we work with the eBrains data sharing initiative, we were also, of course, curious to see if linking publications to data sets has any influence on the impact of the publication. So here we queried to compare the citation count of all the publication in the SKG versus the citation count of publications that are documented by datasets. So we can see here that the number of products that are linked to datasets is quite less. And the reason behind this could be that data sharing hasn't been as prominent as sharing research articles. And also this could be because of the poor data citation practices. The researchers don't often include the full DOI of their datasets when they're citing the dataset. Nevertheless, we found that the citation count for these publications that are documented by a dataset was higher than the citation count of publications in general. This information, of course, needs to be analyzed with similar sample sizes, of course, but having a platform like this to perform such queries enables researchers in figuring out ways to make their research impactful. And in addition to all the queries, the Avant graph in the SciLake ecosystem also provided us analytical power to perform algorithms such as PageRank, as Seraphim mentioned earlier. PageRank is something that is used to find the influence of a product. And it is usually used to rank web pages based on the number and quality of their connected link. And here we have used it to find the 10 most influential publications in the graph based on the PageRank score. And this is our result of the top 10 influential publications in the neuroscience SKG. And to conclude, what we have observed is that linking the heterogeneous research products via semantic entities and bibliographic relationships improves discoverability and information extraction. And our work underscores the need for broader adoption of persistent identifiers, especially in cases of author identifiers such as ORCIDs. If it's well adapted and well put out into the world, it'll be easier to then measure the impact of an individual author in a research field. And then we also suggest that there is a need for improved citation and reference practices. But taken together, these the demonstrations that we show here position the SKG as a powerful foundation for more connected and reusable research in the future. Thank you.
Thank you very much, Archana. And thank you to all the pilots and technical providers that showcased the SciLake result and provided additional insights. So I shared, first of all the presentation will be deposited in our Zenodo community. So I've added the link in the chat, so you can find all our resources there and on the SciLake website, of course. Since we are running a bit late, I would like to propose to address any question you may have in the Q&A, and our partners will be happy to reply. But as we have another panel scheduled in a few minutes, I suggest we take a 5 minutes break just to breathe a bit, and we can be back at 11:35, and we start with the second panel. Thank you again to all our partners that contributed to this session. I wish it could be applause feature. Thank you so much. I'm sure all the audience is applauding you now. Okay, see you in 7 minutes. 8 minutes. Okay. Bye. Let me stop sharing, and can we set up the panel? So Natalia, I'll hand it over to you to introduce the panel.
Hello.
And
Okay.
hi.
Let me see.
Oh,
I'm
blurred.
So it's the camera. Okay, let me see. How can I solve this issue?
Funny though. You look like
it's a natural filter. I think I saw Andreas on the other side, not in the panel thing here.
No. Andreas is here.
Okay, good.
Have I joined the wrong way, or?
Okay, good.
Oh, good. Okay.
So I'm really happy to see, first of all, I was really happy to see the first panel, which covered a lot of what we were planning to discuss. Okay, but so we'll need to improvise a bit now. And then I'm really happy to see all these results from, from the communities, especially from the communities and the technologies. Now, how can I let me try to say, what is what we hope this panel will be about is that we have close to 50 minutes or less now, Stefania.
No, 50 minutes. 50 minutes.
Okay, so we have plenty of time to talk. So what I wanted to say here is that, okay, we talked about knowledge graphs, we talk about LLMs. What I see here, and I'm usually putting my open air hat now on, is that, from scientific information, we have, now more open research information than any point in history. And then, you can, Bianca, you can, I know that, you can contradict that or not, but I think, we have made a lot of effort as the communities to open up many things. Okay. So this is now as we heard in this first panel, we have knowledge graphs, okay. We have AI, but what we also saw is that all of these tools, from the point of scientific rigor, if you want, is that we still have problem discovering. I'm the best user of LLMs, that I assume that they use knowledge graphs behind. But when I'm trying to do a good search and request references and how they reference in the evidence, I get garbage, okay? So we're still a long way from there. On the other hand, we have knowledge graphs and AI machines that they are, we have the AlphaFold, we have all of these super duper things that work a lot very well in structured data, okay, and they produce results because proteins, if you want, is a structured data. So this is the concept, that I want to put here. So what we want to see is that, here is about the intersection of policy, infrastructure, because no one talked about infrastructures in the previous channels. We talked about technologies, we talked about content, but no one touched upon the scaling fact that I want to touch, okay? So let me introduce briefly the four panelists. So we have Bianca Kramer, who leads the Barcelona Declaration on Open Research Information. I think, in the community now, everyone knows Bianca. And also, I know Bianca as, may I say, as a data scientist in scholarly communication. Okay, so this is where you're coming from. Then we have Francesco Osborne, okay, that you lead the scholarly knowledge mining at the Open University. We've seen your work. I've seen your work in the computer science knowledge graph, for example, and I know you're doing a lot of it. We have Nick Jakovic. I'm pronouncing it correct, okay. Now, from the other side, not from the content, but from the technology, who is an assistant professor at TUE, and you lead the graph databases and query performance and the avant graph that people discussed before. And then last but not least, we have Andreas Kolliger. Am I pronouncing it well? Okay. That from your resume, I see that you have designed system for NASA science missions, built medical informatics for rural communities in Zambia, and all of these nice things that everyone wants to do. And now you are leading the applied AI research at Neo4j, okay? So I guess the representative, and I've changed my questions since yesterday, Andreas, they're not very super technical. And I have to say, one is that because of community, because of workload, this is, the first time that we meet with the panelists, so bear with us, okay? So, okay, now this is the context, this is, the introduction. So let me start with the question, because I don't want to go to the technicalities of, the SKGs, but is that, what we've seen today is we've seen a lot of involvement, as I said, lots of open data, lots of open research information. And then what we are hearing is that, and what we are observing is that there's lots of going on. New agents, agentic AI, new knowledge graphs, new LLMs, new this and this and that. So from discovery point of view, is that, where we are now, okay, what is the biggest bottleneck still standing between what a researcher has today and the breakthroughs that we are looking for in research discovery, because knowledge graphs are very good for that. So, I want to start this, with a question about is that, what is it that that you think, very short, just a key point, so we can continue on and with the discussion. So let me start with Bianca. So 5 years ago, certain discoveries were simply out of reach. Okay, we had the keyword search and everything. Now we have the SKGs, the LLMs, we have the agentic AI going forward. So what is still standing between to go into this scientific rigor that we want to have in these discovery systems?
Yeah, thanks, Natalia, and thanks for convening this panel. In thinking about this, I came back to the issue of trust, and that may not be a something that still stands in between progress, but it might actually be something that has gaining importance? Are there a lack of trust of researchers in the new tools, in the role of AI, or too much trust and not critically assessing that question of rigor that might either inhibit researchers to use new tools and new approaches, or it might cause them to not uncritically adopt new tools for purposes they might not be suited for or in ways that they're not ready for. So I would say trust.
Okay, good. We'll come back to you. Now, Francesco.
Thank you very much. So I think that like 5 years ago, there was still a big problem of access to knowledge. Now we have access to most of this knowledge. It's now our ability to structure and reason on this knowledge, because I think most of these AI systems are still doing quite shallow stuff on, for example, research paper just by taking the paper that are most similar to a certain query and try to do a summarization over it. So especially when we are talking about knowledge graph, is more about new method to structure knowledge, to express knowledge, and to be able to reason and synthesize knowledge in a similar way that researchers tend to do.
Okay, so I hear from you trust. What you say is structure. So we have open data, it's structure that is missing. Nick.
I would like to, so I mean, yeah, I don't want to repeat here. So my main point was related to what Bianca said in trust, but again, probably from a little bit of a different perspective, human verification, right? So at the very end, we clearly cannot trust the output of the current systems and the Gen AI, and so this needs to be verified. And then the question is, to what extent we need to verify it? So in one sense, you know, it's good, you know, because we keep our jobs safe, but the human is still needed to a large extent of this pipeline. Yes. But on the other hand, it is something, yeah, on one hand, we get all of this wealth of information, these nice reports, everything, but we need to verify it. And this is where, this is where we are. This is where we still need people here.
Okay. I see what you're saying. Okay, Andreas?
I'll be a little more mechanical about it. Just this past weekend, I was at Oxford University at their AI Society chatting about things. And I was reminded that for the non-computer science part of the crowd, their biggest challenge was just data ingest. And there's a specific example of this economist who's doing historical research, and he had all these papers that were handwritten with tables. The worst case scenario of like OCR on handwriting plus tables, and tables themselves, even in the best of PDF circumstances, are notoriously difficult to actually turn into real data. And so there's some unsolved problems just on the data ingest side, that there's still, as much as we've done good work, there's still a huge amount of volume of data available that we have not actually made manageable yet.
Okay. Okay, so so this is a very good point that takes me now to what I wanted to to elaborate a bit, because all of you touched upon it, is on the raw material, as we say, because we know it's garbage in, garbage out. Okay, so this is the key thing here, and this is where the society, when we talk about AI and SK, in knowledge graphs in general, they don't get it still, because it's a system, but it may be coming in. But science is a bit different. So let me start with Bianca now, because this is where Barcelona Declaration and the community is important. So Bianca, is that a lot of the stuff that we do relies on metadata, and then the community, on scientific community, we rely on papers. Okay, but now we get data, we get software. We know, for example, how the GitHub and everything, that they have all of these structural languages, and how the Cloud Code and the codex and everything is super duper nice. But research software also is a bit different. It's not just, writing a piece of web browser. All of this, what we realize is that there is a lot of discussion in the Barcelona Declaration, sticking to the facts of publications, OpenAlex, OpenAirGraph, and the usual stuff that we do. Okay, how do we go beyond that, and what is needed to go beyond that? Because, Andreas talked about the tables, OCR and tables. Even the tables now is that publications are there, metadata is openly available, but what about the data within the publications, like a table, like a graph? So where do we go from there? If we say that the data is the fuel for what we want to do.
Yeah, maybe also on
that was a long question, but I'll try to keep it short.
What I'm trying to drill it down a little bit. I think a couple of things. First of all, like you say, the materials that are not usually included in knowledge graph. We also heard in the previous part of the meeting, policy documents, all kinds of grey literature. I would add indigenous knowledge materials. So other materials that are not usually part of graphs, information in materials that's not part of graphs, like you say. But I also want to touch upon the statement like the metadata. Yeah, we do have the metadata. And I would say in many cases, we don't have the metadata yet. And that's growing, and that's where OpenAIRE is doing a lot of work, OpenAlex is doing a lot of work, COSAF is doing a lot of work, but we still see that we're missing large chunks of metadata. Abstracts are an important one of that. If we don't have access to the full text, we should at least have access to the abstract. In some cases, abstracts are more valuable, I would say, for some purposes. But we do see that those abstracts are being actively held back. And I think that's one that's very directly related to the rise and the growing importance of LLMs and AI, that it's becoming more profitable for publishers to keep hold of those abstracts and not make them openly available, and thereby limiting the metadata that is available in open knowledge graphs. So I think that is an area of concern. Another area where I see some concern is that while we focus very much on persistent identifiers, and rightly so, because they enable linking research outputs unambiguously, we do run the risk of limiting too much, for instance, by only focusing on materials with DOI, because they have DOIs and it makes it easier to make all those connections, but then leaving out the large set of research outputs that might be lacking DOIs or might have other identifiers. So I think being inclusive in that and trying to also include these other types of materials, these other types of identifiers, and thereby enriching knowledge graphs, I think that's a very important part.
Okay, so this is in the scope of Barcelona Declaration, I guess, right?
Absolutely. On one hand, the importance of that metadata being openly available, also where it's currently not, and also the importance of like diversity and not being selective in what you include.
Okay, so now I have okay, it's good to know. Now I have a question. I will revert a bit the questions that I had is for Nick, is because Nick, is that we're talking about metadata and we're talking about structure, okay, and you're building technologies in graphs that they rely a lot on structures, right? Structured data. So from a systems perspective, okay, how do you treat this, lack of, of good data, metadata, and structure? Where is the trade-off between, from a technical point of view? Because then I will ask Francesco: where is the trade-off between technical, between data structure, and you hear the bell ringing, the data structure and the data quality?
So thank you for Natalia for this question. It was actually I'm still undecided how to answer this question, actually, because there is many interpretations. So let me try to touch upon several of them. So for example, one way, so on one hand, you have the data quality problem, and that typically refers to, okay, some mistakes in data, problems with keys, problems on data items. On the other hand, you have data structure, and that probably typically refers to the topology, let's say, of the data, right? So the connections between the entities and so on. So both of these problems in both of these parts can be thought actually as a general data quality problem, right? I mean, on one hand, you have problems with your, let's say, attributes or clearly data items, strings, and so on. On the other hand, you have problems with your topology, with your connections, missing connections, mismodeled connections, and so on. Both of these are important. And the thing is that from a technical perspective, resolving these problems at these two different layers, sort of topology versus data, it entirely depends on the application domain, right? So sometimes it is easy to fix your, or infer the connections, let's say, right? So fix your topology. And it is more difficult to fix problems in your data attributes. Just because your pipeline, the document is not reliable, let's say OCR is not reliable, or data just doesn't exist, right? And you don't know how to interpret this. And on the other hand, it might be easy to actually fix problems in data. You improve your OCR pipeline, let's say, this then updates your data properly, but then the connections are more difficult. So that's sort of one perspective. But another perspective, if you think about structure versus data, is probably refers to schema, right? So more of a data modeling exercise. So for example, you can, if your data is has incorrect structure, right? So modeled in a certain way, and that also, I think, goes back, Natalia, to your question to metadata, what Bianca also raised, is that sometimes it's your data model, and the data model you put your data in is not expressive enough for you, not only not to store the information, for example, metadata, but also, and if it's not there, your data quality is not going to help, right? If your data is not in the right model, and then you cannot, obtain those insights that you're looking for, because you just don't have it in your data, right? So, yeah, both of these are interesting. Entirely depends on the domain from a technical perspective.
Okay, I see what you're saying. Okay, I should have gone to Andrea, but because of Neo4j, but I will stick because I have another question for you. But I want to hear from Francesco is that, how do you treat this? Because, okay, we have the technology one-on-one graph, we have the graphs, we have all of these nice technologies. We have what Bianca said is incomplete metadata. We have, lack of access to data itself, okay? And then you're building the knowledge graphs. So what, I know from Paolo, if Paolo was here, I know what he would say about, his everyday life, right? But how do you treat it?
Yeah, it's challenging. I think we are moving in the right direction, but slowly, and we are not there yet. And just to list some of the issue that we need to face when we concretely, as you mentioned, build a knowledge graph, I think, the first boring one, which is the super boring problem, and for this reason, nobody wants to tackle, because researchers don't want to tackle boring problem, is simply data quality. So even in the best data set, you find duplicated author, fragmented affiliation, paper linked to the wrong thing, and so on. This is just a technical problem. This is not a research problem. But in the end, if you don't have a solid infrastructure that take care of this, nobody will care, because, we will care because the final result will not be good, but nobody will take the time to solve because it's expensive, it's not original, it's not a cool problem, but it's there. The second big problem that we have, I think, refers to something that Bianca already mentioned, that is this very shallow representation of the content of a research paper. In most metadata that we get, research papers are characterized by these shallow terms, such as a few keywords, such as a very high-level research category, and these are not very useful when you want to answer deeper questions about research. What are the scientific claims? What are the tasks? What are the methods? What are the material? What are the data sets that are being used? And so on. And this means that in most concrete case, if you want to build a knowledge graph that really will aim to answer this question, you need basically to start from scratch, to start from the text, to go to the text and using some NLP to extract information. You also do some of that in your project. But this is a bit of a failure because it's like we already have metadata, we already have a schema, but we say, not good enough, and we need to start again from the text. And maybe just a very, very last bit for me not taking too much time, is that we have paper, but we are also missing a lot of parts from the research process. So we don't have much information about the software, about experiment, about peer review, and so on. So I think we need to think as in terms of community, in terms of future infrastructure, also how we get all the pieces of research that are not exactly reported in research projects, in a research paper, sorry. And this is also about incentive, but I think we will talk about incentive later.
Later, okay. I have to say that, I was very young when, the discussions of metadata were prominent, and, I'm getting old and still, we have the same, stories. Now, Andrea, okay, so, the question for you is that, okay, data, metadata, structure, data quality, all of these are issues that, we care about, and we are using AI and LLMs, to structure our metadata because somebody did not bother to put it there. Okay. So, but, where do you see, because if we stick to the scholarly communication and scientific processes, is that, the community knows about the interventions that we need to do, people and where people fit in. But most of these interventions, they stay on paper because I don't know why, to be honest, is because we are spending lots and lots of money in order to fix the scholarly communication chain. So where do you think that, from your experience, where do you think, these interventions can have, some, gains, small gains and winning gains? Because this is from metadata that we do not trust, as Francesco said, from metadata that is bad. So, it really makes the technological solution harder. What is your opinion on that?
So I'll clarify first. From what I understand about interventions, you mean having a human in the loop and having a curation cycle, having more involvement, right? Okay, so a bit more, let's call it oversight than just pure automation.
Yes.
Set up OpenClaw in your Mac Mini and let it go, right? We don't want to do that. Yeah, so I think to be fair, and maybe I'll start with like the previous kind of answers that even with data quality and structure, and there's a built-in assumption, and I know that it's appropriate for this community, where what we care about is actually doing large-scale analysis over like longitudinal studies or something, that we care about like large-scale view of the data, right? And it matters much more. You have data normalization at that level. And personal anecdote here, like when I got into graphs first, I was doing medical informatics in Zambia. That was my little part of my bio. And it was there that I had my graph epiphany. And one of the things the CDC doctor that I was working with setting up this system pointed out to me is that there's a tension we have between epidemiology, so that we can help the entire society like be saved from disease, versus patient care. And for patient care, if you're lying on a gurney in a hallway, you care that the nurse knows the doctor who wrote the note on the piece of paper on your bedside. That is not normalized data. That is poor data quality. But as long as the nurse understands what it means, you care about that data. That data is good data for you, right? So and this is also a bit of an engineering cop-out, the answer is always it depends. How much the data quality depends, what the structure of the data depends. All these things are optimizations and filters over the data set, optimized for a query that you want to perform, right? Like, what is your point of perspective on the data? What is the analysis you want to perform? You shape the data to fit that. It's a very data engineering thing, of course. And so I think where that ends up fitting in for human in the loop for curation, again, it's a question of it depends. The more important the normalization is, the more there should be human oversight, and the thresholds have to be higher. So like in systems engineering, when we talk about internet services, there's like how many nines of reliability do you have that Amazon's going to be up and running? We need that same level, like I think quality of service measure for AI curated data, that like, okay, it has, how many nines does it have? And how many nines does it need for the application that we're actually putting it towards? Sometimes it's fine for it to be somewhat messy because we don't really care. Coarse grain is fine. So it all depends upon the application, is I guess my final answer to all that.
Okay, so okay, I will pick your brain afterwards because probably your work is not just on scientific data like the rest of the people. So this is the comparisons and how how different groups and actors view things is different. Now I want to go to the second part of our discussion because this is something that is it was touched upon, but not very much in the morning's panels, because, and this is something that, we care in open air, is scaling and operations, because this is, we talk about the graphs, we talk about the LLMs, but no one talks about the infrastructure, and no one talks about the responses that our users are expecting. And of course, at the end of the day, no one is talking about, the money and the funding. Okay, so where, who's paying for all of that? So if I can go for that, because I have my personal views, that the infrastructure, as we know, we knew before the infrastructure was metadata. We're building now infrastructure to connect the data, at least from the open air side. But now we need to expand this infrastructure, infrastructure that is provided to others, to include the AI and agentic AI and all of these really nice things. But if I can start with Nick, because the question that I want us to see here is scalability, technical scalability, and also scalability, trust. So do we trust? Because is it the bigger the better? Do we trust it? So if I start with Nick, the question that I put down is that you can modify it, but you can think about it. Is there a gap between the graph query languages, like a Van graph, that can express what they can execute at scale, and where does if there is a gap, where does it show up in practice? And especially, for service providers like OpenAir, like public service providers at universities that we do not have, tons of money to spend. We're not, Andreas, we're not Neo4j. Let's put it this way.
Well, first of all, Neo4j is an excellent database.
Yes,
I would just like to mention this. But so towards your question, so you again, right? So a couple of different perspectives. So starting from your question about the gap between the capabilities of the query languages, and specifically graph query languages, and the actual systems that executed, right? And then with respect to scale. So this is bread and butter.
Before that, when we talk about scale, also I would like to talk about interoperability, because one of the key questions that I would like to see is that, can I just get part of the graph and copy it somewhere with a few graph queries? That is something that is of interest to us. So it's scaling, but also interoperability. Not just a user asking something, but also, a system from a system.
Yes. Okay. So starting from a user perspective, and from a user perspective, let's say we have this, and this is something of a renaissance, I guess, for the graph technology, because of this standard, the ISO standardization effort that happened fairly recently. There is a new graph query language which is called ISO GQL. And there is also a counterpart to it, which is closer to a relational query language, SQL PGQ. So that means that now we do have, aside from the Neo4j Cypher query language, right, we do have a standardized sort of effort, which helps, of course, also in interop, right? So what you mentioned, Natalia, is that a database practitioners and database engines, right, they need to support the idea is for them to support this query language, just like SQL for relational databases. The interesting question here is that this new query language, it's kind of it's hopes and dreams of users, I would say, right? So what would you like to execute over your graph? And in there, you do have a fairly expressive what I call graph navigation component. Whenever so of course, like one of the things that graphs give you as a first-class citizen are relationships, right? And you would like to exploit these relationships to drive your insights. So you would like to navigate through this graph. And that means you need to look at the paths, right? So not just at the items which are associated with entities, but actual paths and relationships between paths and so on. Now from the graph data engine developer, right, that gives me work, right? Because as soon as you start to look at the paths, as soon as you start to look at the navigation, that potentially can become very expensive, the navigation, because there is immediately exponential blow up of the intermediate results, and so on and so forth. So you need to be very smart in how you execute such queries, how you optimize them, how do you have your indexes, use your indexes in a smart way, and so on. So there is definitely a gap between the expressiveness of the query language and the capabilities of the engines. This gap is closing thanks to the good work, from Neo4j. They are leading this actually effort. Other independent people like myself, right, from the databases. So we're trying to now to bring this dream, right, which is envisioned in this GQL query language, into the realities of such that things actually execute. So that's number one, right? So user perspective. Now the interop. So interoperability, this is, I think, also where the graphs shine because they're more flexible in terms of the data model, right? So the schema could be, unlike relational databases, right? They're more suited for things like data integration, right? So for you, it's easier to sort of navigate the graphs across different systems and so on. So that is a thing, but that is where the graphs are used for. And with this emerging in support query language, both data definition language, how do you define data, how do you load your data, and how do you query the data, the standardized query language, we see that and we think that this will help the interop between the systems. But I must say that this GQL standard is not yet supported widely, right? So this is something which emerges.
Okay, thank you. But then now my question to Francesco and then Bianca, because you're both doing work, as you, Bianca, as a data scientist, Francesco, you're building the graphs, are you incorporating these technologies, these graph technologies in what you do? Because for us, for OpenAir, for example, we need to work with open source software. Okay, and some of these things are too, they're not capable of handling the volume. The open source ones, they're not able to handle the volume that we have, and also it's super expensive to go from one system to the other. So what are your views on that? On this new graph, like Avant-Graph, for example. If Avant-Graph, is the super new trend, let's say, hopefully, Nick, that it will be, how easy is it for us to adopt it? And how easy, that, Francesco, that you're building the graphs and that, you, Bianca, that you're querying the graphs?
I don't know if Bianca want to start or shall I start? Okay. So being a researcher, I'm quite technology agnostic in the sense that I just want concrete result. Indeed, in terms of technology that we use a large range of technology. I think we switched the type of stuff that we use once every 2 years or something like that, because every time for a while Blaze Graph was great, for a while we used Virtuoso, and now we are trying also this more technology that allow us to scale a bit more. So we are looking very interested to this effort from the community to see how we can scale. I would say that also it depends a lot what you need to do. For example, we also do a lot of things that are text heavy, which are a lot of text wrangling. And so in this case, we use text indexes, we use things like Elasticsearch and so on, rather than pure graph technology, just because it's easier. So I would say I'm very concrete on this effort. Maybe I can also mention that I think that in particular in meta science and all this kind of analysis, the good thing about this scaling is that allow us to address issue and to do analysis that will be completely impossible without. So, for example, well, one good thing we talked about before that metadata are not perfect, but actually, when you try to address some of the larger question in meta science, it's okay if some data are not good if you have the scale that allow you to analyze so many research papers, so many entities that allow you to cancel the error. And I see this happening more and more in meta science. For example, in a recent work of ours, we were interested in looking into diversity of research teams. There are a lot of studies in the past if teams that have a certain more diversity in terms of gender or university and so on are more impactful. And these were relatively easy. But we were interested to see, for example, a team that integrate people with different skill would be more impactful. And this is much harder with current metadata. And we were able to do it because we were able to put together OpenAlex and other big open graph that exists today and basically do an analysis. And of course, also your OpenAir. I mean, I don't want to. We use it a lot of them. We use OpenAlex, we use OpenAir, we use Google Scholar, which also is nice because it contains some. We didn't use Scopus because they wanted money, but yes, we use a lot of them. But basically, the idea is when you put together so many information on scale, you start to see pattern, and you can prove pattern with statistical method that would be impossible to see with your eye naked. So in this case, we were able to do some NLP to associate skill to different authors and actually, yes, to prove that research team that integrate different skill, expertise and perspective do receive, for example, more average citation and so on. But these are the kind of metadata study that will be impossible before this kind of technology.
Just because of scaling. And Bianca? Up, you're muted, Bianca.
5 years in and we still do this. Sorry. I think also listening to the other responses, I think the issue with scaling is on one hand, the underlying data, and on the other hand, the applications being built on top of that. And I think there is, when I hear people say, okay, we're going to develop the next thing that will be the next standard, I'm always reminded of that XKCD cartoon that starts with 14 standards and we need one new standard. In the end, we have 15 standards. That's not necessarily a bad thing, but I think that's also what open source data allow. It allows different parties to build different applications on top of that suits their purpose. And I think if we talk about the feasibility of that and the scalability of that, we might also want to look at the underlying data, to what extent we want to bring all the data together in one place and maybe have each new developer of each new organization host all those data locally to then build their applications on top of that, or whether we could also focus on the interoperability of the underlying data to allow to combine different data sources and then build something on top of that. And I'm also reminded of that by from a very practical perspective, and something I've been working on with some other people for the last months is the system where data sources themselves are hosted in different places. And in this case on Google BigQuery, but don't shoot me because I mentioned Google BigQuery, I'll get back to that. But the idea is that, for instance, OpenAir can host their own database on Google BigQuery. And then the Crossref is hosted by Nako Jan in Göttingen. I'm hosting DataSite, Dimensions is hosting DataSite on Google BigQuery. And then for other people who might want to use it, who might not well have the capacity to ingest all those databases and host them locally, they can still query the different databases and combine them using the Google BigQuery interface. They're not paying for the storage, they're paying only for the usage. And I think that as a concept is a very interesting approach to the scalability issue. I think it requires disintegrating the data sources and the users built on top of that. And it also, I think, addressing that part that not everyone needs to host everything themselves. Then, of course, there are follow-up questions, like we all know that Google is not the best approach to that, and many reasons not to want that. But then we can talk about, okay, what is the infrastructure available, the service infrastructure available? can we build something like that? Are there options built on open source that allow also that distributed access to different databases? So that's one area that I think might be interesting to explore a little bit further, keeping the focus on open, but also keeping the focus on usability also for smaller users.
So what I hear you saying, and thank you for the initiative, because it's called
Orion.
Orion.
Yeah. I'll put a link in the chat.
Okay, good, please do. So the idea is that, people were used to using, Google big table, big query, big table, what do you call it? But the thing is that it's not the Google as storage, but it's the big table that, or the big query that is a lock-in, if you want, as a commercial. And Andrea, this is something that is also relevant to, for example, Neo4j, because in many cases, everyone loves Neo4j, but then as public infrastructures, it's something that we cannot really afford to have, the enterprise version that we need with the scale of our thing. And one of the things that I'm the preacher of saying is that as AI and big data is something that we all deal with, we should move into public-private partnerships somehow. So where, there's a win-win situation on that. And, what is your view on that? Because this is something that is of much, is of interest. And that, if you can keep it short, because then I would like to go to the AI and the AI.
Yeah, I think that's a great observation. And it is something that I will say, at least philosophically, Neo4j has always been interested in trying to figure out how to do. That over the years, we've had this internal program called Graphs for Good, where we partner with various outside organizations, both to help them create graphs, but then also host those graphs and do things with it. That has always been underfunded, to be fair. We've never, had a broad general way of getting engaged with us. It's always been, if we have people internally who are willing to do the engagement, then we will do so. But as we move entirely to a cloud-hosted service and less, kind of host your own, it actually ends up being more possible for us to do those kinds of things, because as with any large infrastructure project, we'll have excess, capacity left over, and like whenever we can use that excess capacity in a public, private partnership, that would be a net good thing for us. So that's something that I'm optimistic that we've always intended to do, and that we'll have more opportunity to do as we move forward.
Okay, this is something for me to take, I may contact you personally on that. Okay, so which is good. Now let's move to the, to the third. Stefania, how much time do we have? 10 minutes?
7.
7. Okay. We heard a lot in this morning about SKGs and AI. Okay, and it's not just SKGs, it's KGs, knowledge graphs. But now we talk about science. Okay. What I heard, I heard Harry saying that we always fall back to the SKGs because they give us, they ground the truth somehow. It's something that it is there, but. Okay, we have, let's say now we have the new model of 5.4 in ChatGPT. We have 4.6 in Claude, and these guys are just becoming better and better and better. Probably they're using their own knowledge graphs underneath, but at the end of the day, probably, I don't know, but at the end of the day is that what I find, and I've talked to a lot of NLP and AI people, is that we are fine-tuning our models. We're using, local LLMs together with the graphs. We're fine-tuning the models. We're doing something. We're spending a lot of time. We're benchmarking. We're getting better. And then when we feel confident that we're better, the next model comes and it's better. The next big LLM comes and it's better. Where this is, one business model that we can do. Everyone is using this big tech. The other model that I hear about, that India or China are building are, local LLMs, open LLMs, local that, we can use. But we like this model because we are an open science, we are open infrastructures. But then in Europe, we cannot use these models because, we're not allowed to use a Chinese model. In Europe, we do not produce models. The US are US or Chinese. So where do you see this going? This is something that is of really importance to all of us in Europe, because we talk about data sovereignty, we talk about access to infrastructures, not just to open data, but also to infrastructures. And I think LLMs now are infrastructure, should be part of European infrastructure. Where do you see, maybe I can start with Andrea, because, your job, as I heard it, is AI and graphs in Neo4j.
Yeah, so what you're describing is a real problem that everyone's struggling with, and I'll say all the way to like the AI startups. Everyone who's an AI startup these days has to worry about like whatever unique thing they've got will be irrelevant in 6 months because Claude or OpenAI will just go ahead and replace the need, obviate the need for it, right? So that's a very real problem. At the same time, my favorite sort of quip here is that still the frontier models are generally amazing and particularly bad. In the specifics, in the particular domains, they're still pretty much terrible. And that the only way for them to be great at all domains is to be massive, even more massive than they are today, still 100x bigger than they are today. And that will be increasingly expensive and not really tenable for most people. What we already see in practice, that will always be the case, is that building kind of what's called a harness or structure around a model will always be a 10 to 20% benefit. So that as the bigger models get better, the harness you have around it will make it always 10 to 20% better if you set them up well. That works all the way down to the smaller models, so that if you have a medium or a smaller model that is more specialized, you can always boost that to be basically state-of-the-art for a particular domain. I believe that dynamic will continue. I don't see any way around that, actually, that specializing smaller models will always outperform a general model. And so it's not that you shouldn't have, that you're wasting time with smaller models, I guess. It's how you approach the smaller model. If you make the smaller model and your approach to tuning it and the harness you have around it, if that is an augmentation, then that's always going to be an augmentation. As the models grow, that'll always kind of be a lead ahead.
Okay, thank you. Nick?
I think to add to that, I completely agree with Andreas here, is that one of the leaps that we are now observing is that everybody mentioned this is agentic capabilities, right? Agentic pipelines. But essentially what it boils down to is a tool use, right? So the models are now able to use tools which are given to them through skills or however the provider will call this. But this in turn, I think that this also helps with the smaller models, because as long as smaller models can use these tools and they can use the scaffolding that Andreas mentioned, they will get the accuracy and actually trust. We somehow dropped this topic, but I think it's one of the most important ones. The provenance of information that we so need these days. And by the way, there are models in Europe. I mean, there is one that has been released recently in the Netherlands. So the government is going to be using this. So no, the hope is not lost yet, but I think it primarily boils down to just the insane capex expenditures that this development requires, and the readiness to fund this, right, from different perspectives.
Exactly. I think you're right that in Europe, many countries are developing their models, but I think it's just a bit slower, and the pace is slower, and the updates and everything that what we see and we use every day. Yeah. Francesco.
Yes, what I would say, maybe to be a bit bold, since this is a panel, I think LLM plus knowledge graph is maybe the best architecture that we have at the moment for making AI more robust, but not just in terms of performance. It's not just about, yes, it's 10, 20% better, but it's also the capability to understand, to guide an LLM, to understand what a LLM is using as data source, to being able to correct because one problem is that what if one of this model is wrong? We don't have an easy way to open the hood of the model and to change what is thinking, what they believe, and so on. So using this architecture with LLM plus knowledge graph give us a bit of knowledge that we can actually act on. We can correct, we can understand what is happening, and so on. Actually, this is also the focus of construction knowledge graph in the era of large language model. I mean, so if you're interested in this topic, you may be interested in coming visit us. But the main idea is not just performance, but it's also we can trust more if we have an interface to the knowledge that the LLM will be able to use. And in general, I think that the trend that I'm seeing is some intersection between people using old topological model of reasoning of knowledge graph, embedding, and so on, and dual LLM. And there are some very cool things that are happening, for example, on research hypothesis generation and so on, in which we are starting to see LLM that are really helpful to researcher in real concrete case. That said, yes, it's a problem that big models are controlled by a few big countries. But again, I think that's almost like a political problem. What we can try to do is open the model, share our knowledge, in the end, do what researchers do best. You know, even with not so much resource, we find way to leverage the technology that we have, and sometimes we find solutions that suddenly are much better even the super big model with a lot of money and support, because you know, we are still human and we still have some creativeness, so we can create some good solution with AI.
Bianca?
Yeah, maybe yes to all of that. Yes to the power of smaller models and the opportunity of smaller models. And I think also what you mentioned, that we in Europe might be at a disadvantage. I think we might also be at an advantage if we are like focusing down on that regulatory part. If we are putting more regulation on the openness and the transparency, then and translate that into what we actually use and what we also pay for and fund, then I think there might be sort of a third way of development that might not match like the OpenAI and the Chinese ones in scale, but it might match it in quality and in sustainability. And I should also call out, and Eric Jean-Girard could be able to tell more about it, the models that are developed in France that are fully based on open content and fully based on open algorithms. And I personally think that we should pay much more attention to that and maybe amplify that a bit more.
I think this is a good ending to the discussion, because at the end of the day, we're not talking about only scientific knowledge graphs, but in Europe we care about the openness and transparency. Okay, so I had one more question, but no, I will not go on this. Let's close by some closing remarks from you, all of you. Is that again, we, what as the Nasi said, is that when SciLake started, the OpenAI, was a small company, not something out there. We've seen in 3 years already the growth and the change and the way we're talking now, not just about knowledge graphs that SciLake was about, but knowledge graphs with AI. So if a lot happened in all of these years. So 5 years from now. So when you talk about science, we talk about not more not the bibliometrics. Forget about bibliometrics, but researchers' discovery workflow. What would what do you think that it would look that it doesn't look like today? What again. Let's focus on open infrastructures. Let's focus on trust. Let's focus on graphs and technologies that make it happen. Let's focus on that, that we may have the infrastructure, we may not have, like the machinery available, because that's costing money. Where do you see, things going? So I will start now with Bianca.
I was hoping you wouldn't, but that's okay. I would hope that researchers would have the tools to make this easy for them to be able to benefit from all the additional possibilities to make languages and server things, while at the same time having the trust that these are having the trust of that transparency provide. So not just having to trust on a black box, but also having the option to verify data. And I would add to that, hopefully also building on the small scaling part, that is not just big things, but also that same functionality to discipline-specific knowledge graphs and transdisciplinary knowledge graphs to get that insight. And maybe not by using one big thing, by being able to combine smaller tools and applications.
Okay, that's an idea. Francesco?
So what I hope, at least, is that in, let's say, 5-6 years, AI will become a standard search tool. AI plus knowledge graph, on this big infrastructure, will become a standard search tool in the same way that today we use Word, Excel, LaTeX. Will be simply integrated in the work of a researcher. And for some, we are already going in this direction. And the idea is that we can do things like literature research more automatically, hypothesis generation by exchanging idea with AI and maybe being able to think a bit more holistically, maybe connect different research fields that are not so interconnected because of history of research field, maybe even automated experiment. That would be great, and it would be great for my PhD student. And I think the good thing about that is that will allow researchers to spend less time on data analysis or information gathering and more on creativity, interpretation, designing your research idea. And I want to finish just by mentioning that, again, in the best of possible world, and I know that we are often not in the specific timeline at the moment, you may check why, this tool can also help democratize research. Because with the support of this kind of system, even a small team of researchers, individual researcher, may potentially tackle much larger and more complex questions that now you can tackle just by having a lot of money, having a big team, and so on. So let's hope that we are able to push the world in the direction of this best possible scenario.
Okay, Andrea.
I'll connect two things. One is my favorite aspect about graphs is that, in my view, I love that every node in the graph is its own center of the graph. Whatever its overall graph centrality is, that node matters, right? And then I'll connect that to a dynamic that's happening in agentic AI these days, where memory is incredibly important. And memory starts off as being very simply like, what's the conversation you've had with an agent? But as we move to autonomous agents, memory is really the agent's experience of its environment. And slowly over time, that forms its own worldview, its own world model of the outside world. And that will be increasingly true. We'll see that through this year, probably in action with autonomous agents, OpenClaw and the like. For researchers projecting forward, what that experience actually holds the promise for is that no matter what the global information space is, what we do today by behavior will be even enhanced, that we form our own world memory, and that we'll actually have a codified world memory that we can work within, that can still reach out to the outside world and bring things in. But that research in 5 years from now is going to be incredibly personalized and optimized for what an individual researcher is interested in. You will have your own knowledge graph with its own schema that is self-consistent, that has a mapping to the outside world. And so I think that the possibilities for research are actually going to be incredibly expanded because it's going to be so individualized, which is somewhat of a dream, I would think.
I like what you said, but we can take it offline. Is that that may also hinder people to go into new frontiers. Okay, so think about it.
Love to pick that up.
Okay, Nick.
Well, okay, so Natalia, thank you for putting me on the spot for being last with the closing words. I think, the panelists before me, provided excellent closing remarks. I think for me, like when I've seen this question, when we say 5 years from now, if given this trajectory that the world is going, but more specifically, the capabilities, the research capabilities of AI is going, I would like to bring up something that I heard just recently. I was watching the interview of Claude Code creator, So that's this sort of very, essentially one of the most capable agentic harnesses available today from Anthropic. And when asked with a similar question, you know what he said? He said he brought an example that he used to live in Japan, and he was making miso soup. And I was like, oh, where is this going? So essentially, he said that, okay, if this keeps going, I'll just go back, and because AI is going to be doing everything for us, right? Dario, right, the CEO of Anthropic, promising us the geniuses in the data center, the country of geniuses in the data center, in 6 months' time, right? So the fork is incredibly wide in this case. We don't know. We simply don't know what is going to happen. Mm-hmm. But I will end this on the optimistic note. I think in relation to what all of the panelists mentioned before, I hope that we end up doing things that we feel fulfilled in doing and are happy about.
Okay. I like, first of all, closing this panel, I would like to have, just, 1 minute to say the few words, is that I really like your optimism, because, this is the only way forward. This is, what we need to do. What I keep from the panel is, I keep the trust issue. I keep the data structure versus quality is an issue. So the incoming data, the garbage in, garbage out problem is still persistent. I hear that, we have ways to overcome interoperability. I hear that we have, ways of using AI. But what I would like also to put now in as closing remarks is that in Europe, okay, coming from the open science perspective and running an infrastructure, what we see, what is needed for sure, is that, first of all, somebody told me that this AI race is not a sprint, it's a marathon. So this really helps me contextualize everything that we do. I know that, we need to work on this garbage in, Bianca, we really need to work on that very much. We really need to open up more information that is related to scientific research. We also cannot do that in the AI thing, now I'm speaking, to Andreas, without public-private partnerships. This is now the scale is at this point in time that is not easy for public service providers to do it alone. So unless we have this going together, not much is going to happen. And then what I see is that we talked about researchers, but we did not talk about the role of institutions and national authorities here, that they really need to have to intervene. I mean, we don't see that happening in the US. We don't see that happening in other parts of the world. But Europe, this is where I think, and I'm looking at Bianca now because she's the policy person. This is where, our best bets are come. Now, so Stefania, thank you also much for, doing this. I really enjoyed the conversation. I really need to see, I've seen all of you in person apart from Andrea. So, Andrea, at some point in time, we should meet. Thank you so much for inviting us, Stefania.
Thank you, Natalia, and everyone. This was a very interesting conversation, and thank you for sharing your vision about where we are going now. We are a bit late, so I will just I want to ask Thanasis to share some closing remarks, and I'll release everybody.
Thank you, Stefania. So first of all, thank everyone that contributed to this particular event. I think that we've had a lot of interesting and vivid discussions, and I hope that everyone that participated felt like they kept something important and interesting. Now, I would like to say that throughout the journey that brought us here, it has been, in general, a truly interesting and enriching experience for me, and I think for everyone involved in the project. Don't forget that although we had a general discussion today, We were here also to celebrate the completion of the project in a couple of days and the project results. As we close this cycle of this project, for me, there is, of course, this strong sense of completion in seeing the work that we did and the ideas and the collaborations come together. But of course, at the same time, moments like this that we are approaching the end of journey can be really sentimental. So again, I think that during this 3-year course, we had interesting collaborations, interesting discussions, and I'm sure that some of the outputs of this project will remain useful, at least for some communities and stakeholders. So I would like to close with these words and thank everyone again. And I hope that very soon we will have some chance to work together in another context.
Thank you, Thanasis, and thank you, everyone. We will share the recording, the presentations with every publicly, and we'll send a reminder that the links are out to all the registered participants. So, see you soon, and have a nice continuation of your day. Bye.
Bye.
Bye. Bye. Thank